I'd like to once again request all guests to occupy the center of the auditorium. So, Swagatam, welcome and good morning to all distinguished guests, scholars, and researchers, and our respected faculty members. Welcome to IEEE IES Day 2024 celebrations, Research Conclave for Industrial Electronics, Automation, and Power Electronics, organized and supported by IEEE Bombay Section, Joint Chapter PELS, IES, and Bharatiya Vidya Bhavan, Sardar Patel Institute of Technology. My name is Samrit Shetty, your Cultural Secretary and your host for the day. For the unaware, IEEE is an international non-profit organization for professional engineers. IEEE provides a forum that engages in the worldwide advancement of all forms of technology that relates to the use of electricity. In 1976, the Bombay section was established and currently spans across the states of Maharashtra, Madhya Pradesh, and Chhattisgarh. I'd now like to invite our guests, Dr. Mukul Chandorkar sir, Dr. Shashank Wekhande, and Wekhande, my bad, and Professor Ashok Saraf, as well as Saurabh Mehta, Mr. Saurabh Mehta, Secretary of IEEE Bombay, Mr. B.N. Chaudhary, sir, our principal, and Rajendra Sawant, sir, the convener of our program for the lamp lighting ceremony. I'd also like to invite Mr. Y.S. Rao, sir, our dean. Delighted to call upon one of our talented students, Shriya Inamdar from SE for Saraswati Vandana.
या कुन्देनु तुषारहार धवला या शुभ्रवस्त्रावृता या वीणावरदण्डमण्डितकरा या श्वेतपद्मासना या ब्रह्माच्युतशङ्कर प्रभुदेवः देवै सदा वन्दिता सरस्वती भगवती निःशेषजाड्यापः. Thank you.
Thank you, Shreya. I'd now like to request Principal Sir, Rao Sir, and Talle Sir to welcome the guests to occupy the dais. Welcome Mukul Chandorkar Sir, Ashok Saraf Sir, Professor Ashok Saraf, Dr. Shashank Wekhande, I'd now like to invite our principal, Mr. B.N. Chaudhary Sir, to say a few words.
Good morning. On the behalf of entire S.P.I.T family, I welcome you all and really appreciate your presence here on the Saturday. I know how difficult it's for Mumbaikar to be at some function on Saturday. For us, day is not of 24 hours, it's 21 hours. 3 hours we spent on locals. And in spite of that, such a good number, I really appreciate that. I am so thankful to all the guests here, esteemed guests, esteemed speakers here, for accepting our request and showing their willingness to deliver a talk in today's enclave. I must thank IEEE Mumbai section, Bombay section for trusting us, bestowing that trust on us. We will do justice to the event and try to make a meaningful one. All support what IEEE Bombay section has given, we really appreciate that support, and whatever financial support and other support is provided by section. We are mobilized. We are grateful to you, sir. Thank you, Mehta, from IEEE section. Thank you, Tail, our own sir. Thank you, sir. I will not speak anything on topic today on industrial because they are esteemed speakers. In Sanskrit, there is a Subhashita I studied in high school. Khadyato dyotyate tavat yavat naudiyati shishi. That insect of light has existence till the moon rises. The moment moon rises, that existence is lost. So has happened with me. with Shashank and Mukul sir on and Ashok on dais. Uh, I have no existence in this domain, so I will not speak. I just request. I have just observed how this field has grown up. I remember those days of late 80s when where I had this subject power electronics in my curriculum. We had only two books, Ramamurthy's book. He was Lipo student, TA Lipo student. And then we had another book, Sugandhi and Sugandhi. Those were only the two books in the library for power electronics. This was a tough subject for us. And at that time, if I stretch my memories, hardly 3 or 4% of power we use would come from a power electronic gadget. The word has changed a lot today. Almost every watt we consume is coming through power electronics. Look at all lighting here. It's not direct, it's coming through power electronics. The footprint of power electronics in human lives has gone up exponentially. So is the share of power electronics in the economy because all gadgets have power electronics. And this is going to increase. The way in which world is moving, I'm clearly saying this footprint will increase. And just like today, what has happened with the water, you don't drink direct tap water. You won't consume direct power coming from the grids. You will have in between power electronics, milliwatts to megawatts. I mean, the range has expanded, and that's why uh, we have chosen this topic for this conclave. It is emerging. It is a confluence of all different branches. It hasn't remained one branch now. All branches are merging, all domains of electrical engineering are merging in this subject. You have to know signal processing, you have to know embedded and VLSI, you need to know FPGA, lattice controllers, you need to know control algorithms and deploy them on the embedded boards. You need to know device physics, you need to know sensors, and everything together becomes a power electronics bouquet, right? So I have only this superficial view, right? A deep dive these experts will take. I wish, I hope this day will be, you will have many, many takeaways. I'm sure about that. I request Professor Mukul Chandorkar to declare the inauguration and declare that this conclave is open.
Thank you, Professor Chaudhary, for all those nice words. And as he was also saying, thank you all for being here on a Saturday and being here to listen to these talks and participate in this event. So now I think I should officially declare the event open. So we can start now. Thank you.
Do you want me to hold the bouquet while do you want to hold on to it?
हाँ ओके जो भी है इनको भी इधर से स्विच ऑफ द माइक Before we start the first session, I'd now like to invite Mr. Saurabh Mehta, the Secretary of IEEE Bombay, to speak a few words.
Thank you. Uh, Very good morning to one and all. On behalf of IEEE Bombay section, I would like to welcome you all. Thank you all for coming on Saturday, as sir said. And before I start, I want to thank wholeheartedly to S.P.I.T management, B.N. Chaudhary sir, Sawan sir for organizing such a wonderful event and helping us to actually spread culture for the research. So in Bombay section, we are taking many new initiatives and we try to address to all different kind of audience. We do many programs for undergraduate students. We do many programs for industry people. We do many leadership program, and in all those things, we were always thinking about like PhD scholars and research scholar. And thanks to Kiran Talele sir, we started with this particular like initiative. This is the fourth edition of Research Conclave. Every month, actually, we are doing Research Conclave with a different theme. So this is a fourth actually edition, and in this particular edition, we are focusing more into like a power electronics. The first we started with a wireless communication. The second was related to industrial application. Third was photonic. Recently, just we completed. This is the again power electronics. The next month we have industrial application and AI, and after that we have a robotics. Then again it's related to defense technology. So likewise, there are different themes, and every month we are organizing this event, and this event's actually been hosted by different colleges. So I know that there are many people from different colleges. If you like to host this kind of like a program, be in touch with us. We'll be more than happy to collaborate with you. And the idea is that with this kind of like a event, we wanted to bring industry people and research scholars together and help them to improve their research, not just from the academic point of view, but also from the industry point of view. Because what we have seen in last past edition is that many researchers, they were like giving us the feedback, and they were very happy that they got many ideas from the industry people and how to make their research more application oriented, which is actually required by India. So that's the idea behind this particular like a program. And thank you everyone, and once again I welcome you all on behalf of IEEE Bombay section and S.P.I.T. I also consider myself as a part of S.P.I.T because I have been involved in many programs which S.P.I.T has organized. And I hope that all of you have a wonderful learning day ahead. Thank you.
I'd now like to invite Dr. Mukul Chandorkar sir, Professor E Department at IIT Bombay, for his session on digital processors and debug methods for industrial control systems.
good morning everyone again, one more time. We already wished a good morning earlier. But so I think let me just start out with the topic itself. Uh, this is, so what I'm going to talk about is debugging frameworks for code, for processors, digital processors meant for power electronic control. Basically that. And as Professor BN Chaudhary was also mentioning in the morning, when we talk of power electronics, it's a very diverse kind of a field. You know, it's not just the power devices or the power electronic circuitry or the control methods, it's all of these things together. And part of, and a very critical part and increasingly critical part of power electronics now is the way the control systems for power electronic converters are implemented on digital processors. Yeah. So that is, it's a very sort of niche kind of an aspect that I'm going to talk about right now, and specifically concentrated on debugging of real-time code, so to speak, of real-time applications. So I mean, you're trying to debug code as things are happening in the processor itself. So am I audible? First of all, can you? It's no, okay. It's okay, no? Yeah. So that is what I'm going to talk about, and this way, up or down. Oh, I messed up. Okay, got it. I got the hang of it. So I mean, this is a scenario that we are going to take. Well, this kind of a scenario, power electronic scenario, is what we are going to take a look at, where it's very easily recognizable to power electronics people. That is a drive, yeah, induction motor kind of a drive, where you have a rectifier and then you have these the inverter and then the induction motor. And we are going to take a look, well, the situation that I'm talking about here is when you have vector control, where the algorithm itself is relatively complex, and therefore the code that runs, that implements that algorithm on the processor is also complex, and you're trying to debug that kind of a code while the application is being developed. That is a scenario that we are taking a look at. And typically the smallest time step that you have for the code cycling time is 25 microseconds or even less these days, which is not too much of a time. And so that does put a bit of a strain on the debug methodology, because you're trying to debug something that has a repetition rate of 25 microseconds. So that's what we are going to, the scenario that we're going to look at. In addition to that fastest 25 microseconds or less cycle time that we have for the control code for the drive, we also have other tasks that are taking place at slower rates, and a multiplicity of such tasks. You know, for example, temperature estimation of the motor, looking at whether the motor is in an overcurrent condition and things of that kind. All those things need not take place at 25 microseconds. The code that is implementing that functionality need not repeat at 25 microseconds, but it does repeat at slower rates, 1 millisecond, 10 milliseconds, 1 second, and so forth. So there's a lot of code that is involved in a motor control application. It's not just one long loop that goes through, it's a multiplicity of loops that sort of go through at their own rates. And so as an example of what those rates are, oh, keep on messing up. Am I doing so? How do I go up? So I haven't got the hang of it yet. Lightly, huh? One finger. Okay, I'll try that next time. So I mean, this is the typical timing needs of a motor control kind of a code. Yeah. So as I was saying, 25 microseconds or even slightly less is the numerical integrations that go into solving the motor dynamical model, and then 100 microseconds for speed estimation. The code that implements the actual speed controller runs at a repetition rate of 1 millisecond. Then 10 milliseconds for parameter estimation, how temperature is changing, the resistance in the motor, and things of that kind. All the way down to 1 second, where you try to estimate the motor temperature by looking at its current and having a thermal model of the machine built into the processor's code. So all of this essentially results in thousands of lines of code, yeah, and all of this is running on the processor at its own different rates. So all of this is basically orchestrated by a scheduler. Typically, a real-time operating system works on all of this. And the scenario that we're going to take a look at is essentially how do you debug such code. That's what we are looking at right now. So we're going to take a look at the structures that processors provide, as well as structures that you as a code developer can include in your code that allow you to debug the code. And the debugging activity is useful in multiple scenarios. It's not only at the development phase. Well, I mean that is obvious. Whenever you're developing an application or a code the first time, you obviously need to have debug capability because things never work. You always need to fine tune them. There will be problems with the algorithm. There will be problems with the code is written and things of that kind. At that stage, of course, you need them. But once you have that functionality in the processor, you can also make use of it in the field. So for things like upgrade of code, remote upgrade of code, and field debugging if something goes wrong with the code or something of that kind, all that functionality that you have built into the processor and the code at the time of development of the application itself is useful later on as well. Yeah. So let's take a look at those debug concepts. Is that right? Okay. Yeah. So I'm going to take a look at a specific processor here, Texas Instruments TMS 320F28069, just to have something to pin down on, and the way the code is sort of executing in this. So this particular processor, in addition to have multiple possibilities of threads running on the single core, also has an additional core inside it, a coprocessor core inside it that allows you to run threads in hardware as well. Now all of this has to be then debugged. Yeah, that's the whole scenario. So you have a main thread. So now I'm showing through two threads here. So the main thread that is implementing motor control model, all that kind of stuff. And there's an auxiliary thread that goes on in the coprocessor that is initiated by the main thread. Yeah, so there's a lot of code that is being executed in at least two pieces of code in parallel, while this main thread is being interrupted several times to sort of have multiple threads going on in that in the whole thing. Yeah? So there are these two scenarios, the two pieces of code that are running simultaneously on the processor, and this one large piece of code is essentially broken up into multiple cycle rates. That's the scenario that we're looking at. Now, in all of this, we need to essentially debug that code. That's what we are talking about, yeah. And I'm going to take a look at the various frameworks that are possible in this. Up or down? Yeah, okay, there we go. So, so I'm looking at a scenario where when you're first developing the code for the application, and here is a processor, and here is the host computer at which you as a developer are sitting, trying to figure out what is going on the processor. Yeah. So if you have any questions, please feel free to ask at any time. I think that's the best. So you're sitting. This is your computer, and that's the target system where the code is running that you're trying to develop. And in the middle here, you have a piece of hardware and software combined, which I'm calling the debug controller. Yeah. And that interfaces the target processor board that is implementing the control system with the host computer where the debugging activity is taking place, code development and debugging activity is taking place. I think many of you might be familiar with this kind of a scenario, right? Texas Instruments has this thing called Code Composer Studio, and there are other. Are people familiar with Code Composer Studio and workbenches and things of that kind? So that's what this is, Code Composer Studio here. And then somewhere in the middle you have a piece of hardware and software combined, which we call the debugger. And then here we have the target system, which could be a Launchpad or one of those standard boards or whatever. That is the scenario that we are looking at here. And we want to do the debugging in real time while the code is actually running on the processor. Yeah. we want to do it with as little intervention into the working of the main application code as possible. Yeah, because I mean, any act of interfering with the code execution to try to figure out what the code is doing is intervention, and then that disturbs the code flow, that disturbs the application. Yeah, so we want to do it with as little disturbance to the code as possible, to the application code as possible. We want to debug that code. Yeah, so there are several ways of doing that. I mean, perhaps one of the easiest is to embed an instruction in the code that says toggle a pin, and then you know that you have reached that point. But that instruction itself is an intervention. It's not part of the real code. It takes time, and when you're looking at 25 microsecond kind of time steps, that does have an impact. So putting an instruction that says toggle a pin and toggle it back when you've finished at some other point, and looking at the output of the pin on an oscilloscope to figure out how the code is working, that is interventional. Yeah, even though it is a good way of doing things, you're still intervening into the operation of the code. Yeah, and there are different levels of intervention that are implementable in a code, and that's what this is what I'm going to take a look at as we proceed further. Yeah, but that is a context. So here we have the target system where there's a processor running the application code, and that target system is a debug port. You might have heard JTAG and things of that kind. Right? So that would be then the JTAG port, so to speak, and this would be the JTAG interface. And then here is the host. This thing, it could be USB or whatever, or Ethernet or something of that kind. So that's what we are taking a look at. This seems to work. Yeah. So those three pieces that we had, the target system, the debug controller, and the host computer, I've sort of mapped on this thing here. That is the host computer where you are sitting and trying to debug the code, and that is typically you run a debugger on it, like the GDB or some kind of thing that is embedded into the Code Composer Studio, and that gives you breakpoints and all a graphical interface that tells you where you have reached and things of that kind. That's all on the host computer side. In the middle there is an external debug controller like a JTAG, some JTAG kind of a emulator, so to speak, that way. And then you have the processor and the debug module on the processor itself. Yeah. And so the terminology a little bit, I mean, so this interface here between the JTAG controller and this one, so to speak, could be either a USB, a UART, or Ethernet. It's very often a USB. You connect a USB to it, and that way. On this side, it has what is known as a test access port controller, TAP. The JTAG has a test access port controller, a TAP, and then the connection here is through the JTAG pins. Yeah, so JTAG or single wire debug. So typically on the what I'm showing on the left hand side of this thing of the slash there is typically a TI scenario, Texas Instruments kind of a thing. You have a JTAG, you have a USB and all that kind of stuff. On the right hand side is more of what you would find in ARM kind of a scenario. So SWD, single wire debug, is on the ARM kind of systems there. At the lowest level, the debug module, and I will take a closer look at the debug module. I mean, how does all this functionality work? At the lowest level, you have debug circuitry on the processor itself that supports the user debug activity. Yeah, and ERAD, I think it stands for Extended Real-Time Acquisition and Debug, or Texas Instruments terminology. And on the other side, ARM has what is known as core site. Yeah, it has core site on the on ARM processor itself that allow you to debug code that is going on in there. Now, the various levels at which debug is possible is what I'm going to quickly go through in the next few slides. Okay, here we go. Now, essentially, there are these two broad categories of philosophy, so to speak, of debugging. One is non-intrusive debugging, completely non-intrusive debugging, and the other is fully intrusive debugging, and in between the two, we have a wide spectrum of things that can happen. Yeah. So let's take a look at the two extremes. Yeah. Completely non-intrusive debugging. Now here is the user program code, all of that motor control software that is going on, right? And the user program code does not know that it is being monitored. That is completely non-intrusive there then, yeah. There is completely non-intrusive debugging. The user program code does not know it is being monitored, but there is an on-chip debug module which keeps on looking at what the user program instructions are doing, yeah. So it observes that, which means that uh, the flow of the user program essentially is in two parts. One is the instruction fetches from memory, right, the machine language instructions coming from the memory, and the other is the data associated with those instructions. So there is program memory and then there is data memory, right. So program memory sends out instructions, data memory sends out data on which those instructions operate, yeah. So these instances that I'm talking about, the on-chip debug module looking at the code flow and then going back and reporting to the on-chip debug module, looks at both these things. So every instruction that is basically fetched from memory, from the program memory, a copy of that also goes into the debug module, yeah, automatically. That is the support that the on-chip debug module gives you. That's built into the processor itself. And the same thing with the data. That allows you to keep a trace of instruction sequences in the debug module, and also a trace of data access inside the debug module, which is basically maintained in a separate piece of memory which is not accessible to the user from the normal memory interface. It's separate. It's not part of the memory map of the processor. Yeah, that's part of the debug module itself. It's basically the entire sequence of program execution is then maintained in a separate buffer that is not in the processor's memory map, that way. Yeah, so every instruction that goes for execution into the pipeline of the processor is also then put into the debug module itself. Yeah, so that's the scenario that happens. That's completely non-intrusive. Yeah, because the thread does not know anything. It does not know that it is being observed. Yeah, and then once you have all that data collected out here, is all happening in real time, you can have an interface to the debug port, the JTAG port, which the external user now can access and look at what's happening there. Yeah, that is so that's what the debug port does. On the other side, the other extreme, we have completely intrusive debugging. Yeah, which means that we do not make use of the on-chip debug capability of the processor, but we write our own piece of software which once in a while interrupts the program code, looks at where we are, reports back to this software, and it maintains that flow there then, you know. And you keep on doing repeatedly and keep a trace of that and then send it to the debug port. So we have these two extremes. One is completely non-intrusive and the other is completely intrusive. And as I was saying, in the middle between these two extremes, we have a whole range of possibilities. Minimally intrusive or minimally non-intrusive. We have a whole range of possibilities. So what I wanted to do in the remaining time is basically just give a flavor of what these possibilities are out here. So you get a little bit of an appreciation of what happens when you connect the JTAG port to this and that kind of stuff. Yeah. So I'm going to start with the ARM. Yeah. So I'm sure several of you will have worked with the ARM, right? So on the ARM, you have this thing called the core site module, and there are several blocks to this. I'm not going to go through all of the blocks out here, but just the main ones. So to be able, so this is an example of completely non-intrusive debugging. Yeah. So I mean, the core site module does what I was showing on the previous slide, where the module is just observing what's happening there. A copy of the instruction also goes into the module and of the data as well, and it's maintained in this so-called the internal memory inside the debug module that maintains the sequence of instructions and data access. So to be able to do this kind of thing, you need two capabilities from the debug module. The debug module is part of the processor itself. You normally you don't access it normally uh, when the program is running. The user program never accesses the debug module, right? It's only the external developer that accesses the debug module. And so for the debug module to work, there are these two critical things that it needs to work non-intrusively. There are two critical things it needs. One is what I was just saying, that it needs to have a copy of the instructions that are going through and a copy of the data that are going through into the main thread, into this buffer there, so that it can be extracted and you can figure out what is happening there. That's one thing, that is basically capturing the instruction flow as it is happening is one thing. The second thing is to be able to send out that captured data to an external debug module, to an external user, without invoking the processor's resources. So you cannot use a UART or something, because that comes under the processor's resources. Yeah. So you need a separate pathway for that data to go out for completely non-intrusive debugging. We don't want to use the processor to initialize some port through which then the data goes out, because then that's part of the processor's behavior. Yeah. And that is where this JTAG comes in. Yeah, the JTAG is a mechanism to get data out of the debug module without making use of the processor's communication capability. No UART, no SCI, no serial communication, no S.P.I., nothing of that kind. It is a separate state machine that is activated by a set of pins from which you can get the data out that was captured by the debug module. Yeah, so these two things you need. And on ARM you also have this thing called the serial wire debug, SWD, yeah, that either a JTAG or a serial wire debug. These are ports that are not in the processor's memory map directly. Yeah, so they do not, accessing data from JTAG or the serial wire debug does not use any processor resources that the main thread is, the user thread is using. So these two things you need. Yeah? One is the ability to capture the flow of the program, and the second is a way to send that information to the user who is debugging the code without using the processor's resources. And if that happens, then uh, then the then the code, the user code, has no idea that it is being observed and information about it is being sent out. And that is the extreme of non-intrusivity that we can have. Yeah. So that, sorry. Yeah. Tell me.
So, even if the main user program does not explicitly use those communication ports,
Yes.
still it cannot be parallelly accessed and used
These
for the
ports,
debugging port.
for these ports, they can be. Yeah. So I think it's okay. The question is whether they can be, whether the JTAG port and let's say the UART can be parallelly accessed. They can be. They're completely separate. Yeah. So it's not mapped into any of the memory map kind of
It's not
stuff.
specific to only the
No,
module.
no, it's not. Yeah, that way. Yeah. So that's what, so that's the basic scenario here. Yeah? Completely non-intrusive debugging. Uh, do I go up? Yeah. Uh, so this is just an explication of what I was just mentioning. We've already gone through this, in fact. I mean, so this is the processor on which the code is running. This is the external debug interface, JTAG or whatever, and that is the host computer. And this is again continuing with the ARM kind of a scenario. Let us suppose that you are debugging code on an ARM M7. Yeah, you want to do that. You can set up the external debug controller on an ARM M4, a slightly lower this one, right? And write a program there which excites the JTAG test access port, pins up and down, drives the state machine of the JTAG, or the serial wire debug, yeah, all of that. And on this side it presents the USB to the other side. So there are several such links available, you know, for ARM. I think there's some ST link or things of that kind. All that basically is implemented here. It basically simply provides you with an API, an application programming interface, that allows you to get data and display it on the other side and that kind of stuff. Yeah, that way. So So that is the sort of implementation of what we were talking about in an ARM context, in an ARM debug context, yeah, with a piece of hardware there. And yeah. So this also we have actually gone through as we were speaking. This what the content on this slide. The host computer and debug processor communicate via standard interface, that is this one, yeah. And examples are USB, UART, Ethernet. And the host computer can perform high-level debugging functions with the data received from the Cortex M7. You can set debug, you can put breakpoints, you can show where it is, you can single step, all that kind of stuff can be then done with this interface. And on this side then you can have a nice graphical user interface that allows the user to push buttons and view graphs and look at the traces of instructions and things of that kind. Yeah, but all of that is essentially coming through this because of the low level debug functionality, non-intrusive debug functionality that we have on the Cortex M7 on this side. Yeah. So now going quickly on to intrusive debugging, the other extreme now. We looked at non-intrusive debugging. Now the intrusive debugging, uh, this is a piece of software that runs on the processor core itself. So we are not going to make use of any internal inbuilt debug module on the processor itself. We are writing our own piece of code, yeah, and that piece of code is a separate program that lives in the program memory of the processor itself, and so is the user program that is actually supposed to be running. So there are these two programs. One is our debug program, and one is the main program that that implements the application, and we switch between the two. And the control of the so during the debugging process intrusively, the control of program flow is handled by the debugger code, our code, the debug code, and it starts and stops the main thread, the main application thread under its control, and every time it sort of picks out things from the application code, the values of registers, the values, what was the last instruction that was executed, and all that kind of stuff, and puts it in a buffer which can then be accessed using one of the standard interfaces of the processor, like a UART or something like that. So both counts of data capture and data communication to the host are now intrusive, because data capture is done by a piece of software that is also running on the same processor as the application code is supposed to be running. And secondly, we are using a port of the processor that is mapped into the processor's memory map, which is essentially also using the processor's resources. So that's the extreme end of intrusive debugging. Both counts that are needed for debugging are then implemented by using the processor's own resources, which resources are also going to be used by the main application program. You know, that's why I call it completely intrusive there then. Yeah, the other extreme of it all. Yeah. Any questions on this or comments? Yeah, please. You don't. No, you don't. That is the whole point. That is all done by the debug module, which is a piece of circuitry on the processor itself, which takes the instruction, the main thread goes, it automatically goes to that one. No, 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 no. There is no user code that needs to be written for that. That transfer is by driving the JTAG state machine. So JTAG is essentially a state machine. You know, a sequence of ones and zeros on pins steps you through the states and gets you to get the data out from the TDO. It's called TDO, I think, yeah, pin of that one, that way. So that is by driving the state machine. It's completely separate from the way the processor's instruction cycles are working. Yeah, that's why it's completely intrusive, non-intrusive. No, absolutely not. Yeah, the user thread does not even know that it is being observed that way. Yeah, is the complete opposite of this, where the user thread is actually controlled by the debugger, because I want to debug, you work the way I want you to, that way. So these are two extremes that I'm talking about. Yeah. Yes, 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 exactly. Yeah, and trying to do it as minimally as possible, of course. Yeah, but still interrupting it all the time. Yeah, and there are costs to be paid for that interruption. So I mean, timing is all messed up. Yeah, timers will count out sometime, and all that kind of stuff will happen there. Yeah. So again, coming back to this, we have already gone through this. I will not spend more time on this, but let me go to the next one. Yeah. So the way, so this is one possibility of implementing intrusive debugging, yeah, by writing your own code, and you can structure your code, the debug code, this way. I mean, see, it's not that intrusive debugging is bad and this is always good. There are trade-offs here, If you do it this way, you have more flexibility. You can customize what you want to do because you are writing the code. If you do it the completely non-intrusive way and stick only to that, then you are essentially constrained to work with only the resources that are provided to you. Yeah, and that's why in between you have this large spectrum of doing things. Yeah, so here you have total flexibility on implementing your debug philosophy, which you don't have when you do it completely non-intrusively. So here, so one way of doing this is essentially to write your write a debug code. Yeah, so the main program is running, and whenever there is a time for the debugger to stop the main program and read out values of registers, instructions, and things of that kind, you enter into a interrupt service routine, and the interrupt service routine can typically be then implementing a command response kind of a thing. It sends a command, and then and then you get a response of the state of the main thread. That kind of a scenario. You can have a command response. There are several possibilities in implementing this. I'm just giving one example of this. Yeah, and so all this is then software that you write. You decide on the protocol of how you want to debug, how intrusive or non-intrusive you want to be, how much of capability you want to have in your debugger, yeah, and then implement it accordingly. Yeah, so this is a command response kind of a framework. Then the debugger sends a command, and then there is a response from the main thread saying that this is the state, that way. Yeah. And some details of that, I'm not really sure I should go into these details. Maybe maybe not so much. I mean, this is just one way of implementing it. I think let us not go into the details of this right now. Let's look at only the scenarios. Yeah. So I'm not going to spend too much time on this slide, but I'm not sure. I mean, these slides will be available, I suppose, right? I mean, you're free to take them from the organizers and take a look at them at leisure. So let me go on to the next one now. Okay, so a variant of this. Now, I'm going to talk about a few variants before I end. Yeah. So we looked at the two extremes: completely non-intrusive and completely intrusive. And now let's take a look at a few variants in between, and what advantages you can get and disadvantages of those. So one variant is essentially if you have a system that has a dual core processor, yeah, but an asymmetrical dual core processor. There are ARM offerings of this kind as well. So one could be a Cortex M7, another core could be a Cortex M4 on the same chip. That kind of a scenario. So this is running the main program, and you're running the debugging thread, the intrusive debugging thread, on the second processor. So at least you're slightly away from having to run the debugging code on the main processor. So at least that you've sort of gone away from that part. So you're running the debugging thread, the monitoring thread on the second core, while the main program is going on there. But the context, the scenario still remains the same. The code running on this will once in a while ask this to send some data, interrupt that code and ask it to send some data. But the advantage here is that the memory spaces are different. You don't need to, completely separate. You don't need to share all the resources on the same processor for this thread and the other thread, the user thread and the debug thread, So then, to that extent, at least it's sort of okay. It works. It's substantially better than the earlier completely intrusive scenario that we looked at. Yeah. So that's this slightly a bit of a variant of the scenarios that we were looking at. And an example of that in the TI world, so to speak, is this processor. Have people been using TI processors, Texas Instruments, at all? Yeah, TMS 320F, 28379, 328, all those kinds of things. Yeah. So this is one of the same family, 28388, in which there are two main cores. Yeah, CPU1 and CPU2 are two cores, and then here you have a Cortex M4. So it's one more core in there. Yeah. So this Cortex M4 core is meant for connectivity, connecting this processor to the external world. But you can also use it for, if you want to set up a user specific debugger, you can write a debugger and run it on the ARM core, like what I was showing on the previous slide. You can write debug code on this, and only the user application code then runs on these two cores. Yeah, and then you can have this interacting with the other two cores and getting information from them and sending it out to the external user through an interface, through a communication interface that is mapped into this processor, not on the other two. You can say that the UART is mapped to this one, and then you don't have to worry about controlling the UART from these two processors as well. Yeah, so the communication is then completely separate, non-intrusive. Yeah, but the data capture, instruction and data capture is intrusive, or try to make it minimally intrusive. So that's one variation that you can have when you have architectures of this kind. And then there are many such. I mean, I think ST Microelectronics, Texas Instruments, many people have these kind of asymmetrical multi-core offerings possible, which you can make use of to implement debug capability.
So that ARM Cortex M4 is not the debug module as such, or
it is meant for connectivity. Yes, so it has so the Ethernet is there, or EtherCAT is there on that. CAN is mapped to that. A couple of UARTs are separately mapped to that. And then
but it can be
potentially used for debugging as well. That's what I'm saying. Exactly. That's right. Yeah, you can run the debug code on this and get stuff from the other two and send it out.
But is there a separate debug module?
There is.
Okay.
So there is a JTAG module on TI processors, but the thing is that so there is a JTAG hardware. I mean, not JTAG hardware, but debug hardware that uses the JTAG to do that. But its details are not published. Unlike in ARM, where the core site details are completely open, public documents, TI does not publish the way its debug module works. So you cannot write your own piece of code that excites the JTAG to bring out all the resources that it is capturing inside. Yeah, I mean, see, there are. I'm not an expert on security, but the moment you have debug capability, you have a security issue as well, because anyone can access that. Yeah, please. Sorry. Yes. Yes. Yes.
Thank you.
Yeah.
It is interrupting many times
Yes.
because might be the debugging is there, some sort of, and might be there is more debugging.
Yes.
So whenever it is changing the topics and it is stopping the processor, and what you are doing, you are putting it into the buffer.
Yes.
That time, because we need to save the codes, whatever the codes are going on, that the buffer is playing the important role.
Yes.
But whenever we are considering up the buffer, there are many registers which are not recognizing that particular bits. Basically, the least significant bits, what I little bit know about it. So that is the one problem when you are doing the intrusion, because intrusion is required.
Yes.
We are doing the debugging while the user doesn't know anything about it.
Yes.
So sir, there is one thing which is the double precision floating point unit is helpful for this while stopping and starting the main processor.
That's a good point. I mean, so potentially all that unit is
Yeah.
also part of the resources that you need to capture and store.
Correct.
Yeah. So, so those registers also you need to store in memory. Somehow.
Right, sir. Right, sir. They are precision type of registers.
Yes,
Yeah, correct.
So you have two registers at the time of 64-bit if you want, so or two 16-bit registers. If you
Yeah, two 16 bits or 64-bit double precision. We are taking 64 bits also.
So all that has to be saved onto, and all this takes time. More than the number of bits, everything is captured, but it takes time.
Yes, sir.
Yeah? So it takes time away from the execution of the main thread. That is the problem. That's the
Yeah.
critical problem. So you have to then stop the main program flow, read its
Right, sir.
snapshot,
Hmm.
keep it in memory, and then let the program flow go again.
So it is not interfering the buffer time, whatever we are storing it during.
Actually, it does, because
Yeah, it does, no?
storage does take time.
Correct.
So transferring register contents into a memory buffer
Right, sir.
is time consuming.
Though we are taking the third layer of cache also,
Yeah,
but still it
everything.
is giving the same problem.
Yeah, it will do that.
Yes, sir.
That's one of the problems with intrusive debugging.
Correct,
You're
sir.
right,
Correct.
absolutely.
Yeah, I wanted to ask you this question. Thank you very much.
Thanks for the
Yeah,
question.
thanks.
But absolutely right. I mean, so saving all those contents in
Yes, sir.
buffer memory does take time.
That's why we are struggling that how to save that time, because you know debugging is
Yeah.
also important, and
Yes.
the stop and this intrusion is more
Yeah.
giving the
Absolutely
facilities.
right. I mean, so I've written this debugger.
Yes,
I
sir.
know how it works.
Sir.
All the earlier command frame that you saw.
Yes,
I
sir.
wrote
That is why very interesting.
The thing is that sometimes you might need to just write that piece of code in assembly language, just to
Right,
make sure
right.
that you do the best you can.
So that
Yeah, absolutely. It has to be written very very carefully, so that you have minimal intrusion, that kind of thing.
right, sir.
You're absolutely right.
Thank you very much,
Sure.
sir. Yeah.
Yeah. So, so this is what I was sort of trying to talk about when uh, when we have this asymmetrical multi-core kind of a thing. Yeah. Uh, there we go. So again, this is elaborating on the same things that I was talking about earlier. Uh, that the the ARM core essentially will then run the debug code and the host communication, uh, and it can read off things from here from shared memory between the cores, and then finally the ARM core then connects to the host computer, has a USB kind of a connection to the host computer or Ethernet, and that allows you to do debugging at the host computer level that way. Yeah. I think that was it. That line means that I'm done. So thanks a lot. Maybe I should move away from this. Yeah. There's something is on here, I think. So any final questions? Thanks a lot for attending to this and things like that. But any final questions that?
Does the mirroring happens of a main core to the debug core?
So
Or code is, I mean, when some application is running on.
yes.
So whether the mirroring of that code happens to the debug core or
No. So if you have a debug module inside, then it happens automatically inside the processor itself, and then your job is to extract that. That's all. The debugger's job is to extract that, and uh, but if you're doing it through software, then you have to ensure that the instruction is sort of recorded, that kind of thing. that way. But as very briefly mentioning, there are security issues in all of this debugging, and I'm not an expert on security issues, but certainly there are issues. So the moment you have capability to access the processor through some kind of a port, you have a security issue. And uh, I really cannot say more about that. I mean, my concentration was essentially on the debug mechanism here, not on how security is implemented, which is better, which is worse from security viewpoints. I really don't know the answers to those things. Yeah. Yes, please.
Debugger, intrusive debugger.
Yes.
Are there any open source debuggers available for
Yes, that's a very good question. There are open source debuggers available for both scenarios, intrusive as well as non-intrusive. So as I was saying, for ARM, uh, the debug module, the core site documentation is public. It's all out. And then there are open source tools. There's one called OpenOCD, Open On-Chip Debugger, which essentially gives you a set of APIs, application programming interfaces, that connect to the pins on an ARM processor to access the debug module on that. That's possible. But for the non-intrusive side, for the intrusive side, uh, it, I mean, I don't think there are any uh, open source tools as such so easily available.
For example, the one that you wrote?
Yeah, I'm going to make it open source eventually.
Maybe the first one?
It, I doubt if it will be the first one. I've not really looked at what else is available on that scenario. But that becomes very processor specific.
Yeah.
That
So
way,
if you're using this processor,
it'll work.
does the Texas or any other chip manufacturer supply source code for?
No, they don't. They don't. No, Texas Instrument
This is
doesn't.
very good.
This is my own stuff. Yeah.
So probably the semiconductor companies may offer it.
Yes.
Nothing like that.
No, I don't know of any open source tools, debug tools for these processors.
It's a good niche.
Yeah,
For the products.
that's true. Yes. So I wrote up my own code for this, for Texas Instruments, especially for Texas Instruments processors, and a bunch of them, a whole family of them. But I'd like to make it open source. Why not? People can use it. Yeah. So we'll do that at some point. Yeah, please.
This debugger code you are written is for specific to this particular core or KKC or
So it's generally for the C2000 family, I would say. Yeah, it works for all of them that way. So yeah, with minor tweaks between variants in the family, the basic code works for a whole range of processors. Yeah, but it will not work for ARM, for example, or it will not work for some Renesas. Or then the moment you do it this way, they will be very family specific, if not processor specific. That's the disadvantage of that. Yeah. So, any other questions or comments on this? Yes, please. Yeah. Hmm. Yeah. I don't really know. That depends on the tool, I suppose, the specific tool that you're using. From yes, I'm not sure. I can't answer that question. I'm sorry. That specific question, I don't really know the answer unless we know some more details of what's happening on that. Yeah. Hmm. Yes. You can't access that. Yes. Yeah. So how to override that is something that I don't really know. Yeah. So yeah. Neither am I. I'm sorry, but yeah, I don't think I can answer that question satisfactorily. Yeah. But Yeah, please.
I don't have a question, but I have a comment.
Yeah.
Particularly when you are going with these two-core type of asymmetric arrangements,
Yes.
in automotive electronics, particularly safety critical and
Yes.
redundancy,
Yes.
we see a lot of applications like this, and within Allegro we go for Cortex and RISC-based processors
Okay.
to do inside coding.
Hmm.
What normally we do other than diagnostic is that when the diagnostic fails, the M4 core will take over the job of the M1.
The big one.
So it is continuously monitoring it, what is doing, what is the state, what are its parameters, and it's storing it for its own diagnostic. But if suppose for some reason it finds that no, my master has
Failed.
died or failed for some reason, it takes over the job from that point inwards, and then it may not be able to drive the vehicle at say 200 kilometers, but at least it will take what we call as a limp mode, where it can
Degraded
drive
mode.
with the
Yes.
slowly and then take it to the safer
Yes.
speed.
Yes. Yes.
So little bit of extension for your diagnostic.
Oh
that
yes,
what we do
absolutely.
is that
Yes.
diagnostic, and then the minor controller is taking care of the controlling the further.
Yeah, absolutely.
So
Yeah.
just small addition.
Yeah, thanks a lot. That's a very important addition. Thanks. Yeah, it's good to know that. Yeah. Yeah. So it can do a fallback if needed, in addition to the debugging.
So it's a redundancy.
Redundancy,
It's
yes.
very critical, particularly for this autonomous vehicle.
Hot standby.
We have a lot of like quad cores we are using nowadays. So not one, not two, but there are multiple cores working together to keep monitoring on each other.
Yes.
And then if somebody goes off the
They can take over the
line, then it
functionality.
can take
Yeah,
over.
that's right. Yeah. Multi-core or multi-processor.
Robust means sometimes you just lose the communication with the master. So
Yes.
the motor driver ECU is there, but the ECU loses the control to the top.
Yes.
What do I do?
Yeah.
So there is a lot of intelligence built into even now these drivers in order to take your vehicle safely and ensure that the vehicle is safe.
Some basic functionality is always maintained that way. Yes. Yeah. Good point. Yes. Thanks a lot. Thanks for the addition. Yeah. So any other questions, or shall we call it quits then? Thanks a lot. Yeah. Thanks a lot.
I'd now like to invite Dr. Saurabh Mehta sir to thank Dr. Chandolkar with the token of appreciation. And Dr. Vyas Rao sir to present this hamper as a welcome. Thank you, Dr. Chandorkar. Now we'll have a paper presentation by Khadija Pathan, who is an undergrad final year from SPC.
Sorry about that. I have to leave.
Hello, and a very good morning to all present over here, dignitaries, faculties, and all the attendees present over here. I am Khadija Pathan, student from final year BTech Electrical Engineering, Sardar Patel College of Engineering, and topic for my research presentation is Smart SCADA Alarm Analyzer for Effective Grid Management. And it is also a project which we are currently working on under the guidance of Dr. Sangeeta Dangade, ma'am, our very own HOD from our department, and Mr. Mahesh Mandre, sir, who is the Chief General Manager from Grid Controller of India. So, firstly, the name is quite big, like Smart SCADA Alarm Analyzer for Effective Grid Management. And it is tough to make out what it is. So I would be happy if I'm just able to make you understand the essence of the project. It might be a drift from electronics, which we just heard, but it's related to grid management and power system and smartly prioritizing the alarms that we get. So going towards the problem statement and how we accessed or how we approached towards this project. Actually, I had my internship done at Power Systems Corporation of India Limited in WRLDC region, that is Western Regional Load Dispatch Center. And there, the main attraction for us was a control room. The control room where we are able to see our electricity grid, live electricity grid, and all the terms and terminologies associated with it, like live power flow, what's happening in the grid, and everything. At the same time, we understood that a control room is flooded with alarms. And what are these alarms? These alarms are basically each and everything that happens in a grid is generated into an alarm. For example, a ICB or we would say a transformer, ICT is taken into service, a reactor is not in service or anything. So we are working on a circuit breaker based project. So for each and every alarm from a circuit breaker, an alarm would be raised in the control room. Firstly, we were handed over a file, a 1-day file, which had a data and alarm set of 7,453 somewhat alarms. And we were amazed to see that and how a operator would manually go through each and every alarm to analyze and figure out like what's happening in the grid. So we came up with this project, which basically aims to emphasize and prioritize the alarms which are most important and generate a meaningful message to the operator so that it's easier for them to understand like what's the situation and what has actually happened in the grid instead of going through each and every alarm. That's what is written over here. And most of the alarms that are generated are not actually false alarms, or maybe due to maloperations of the RTUs, those are remote terminal units. We usually get false alarms, and due to so many alarms, most of the important alarms get overlooked. To prevent this, we have an objective of smartly prioritizing the alarms in a way that the most important alarm will just pop up to the operator and he or she will get to know that yes, this thing has happened in the grid, and it will be more efficient for them to handle the situation. Moving ahead, this is the flow of the project. Firstly, we are extracting the live data of alarms from SCADA systems. Then the program filters out the noise or the garbage data. Filtering holds a key value in our project. Then it is comparing the actual filtered output with the real-time SCADA line flow. And then we would be generating a message for the operator. Moving ahead, this is the approach, and the approach is basically for the filtration of the alarms. In this approach from SOE file, we extract the line name and observe if the opposite end of the extracted name is in the ith events below. For explaining this more clearly, I would like you to glance through this slide. It has some of the alarms that we got in a form of CSV file. And as we can see here, an alarm is generated for JP Nagari Satna line for a circuit breaker opening at JP Nagari end. Similarly, an alarm is generated for Satna JP Nagari, which is the same line but opening at Satna end. So it basically, the logic behind this code is that for a line to be out, the circuit breakers at both the ends should be opened simultaneously. If not simultaneously, at least having a few buffer of time. And if so, then we could conclude that the line is not in service. So this is what I mean by the third block of the power flow. Then if true, a message would be generated. So currently we are working on just lines and circuit breakers and creating messages for line outages. For filtration, we are using two logics. The first logic is checking the pair of circuit breaker openings for ith iterations. Those are 20 iterations which we are taking into consideration right now. And for logic 2, we are taking a time tolerance of 5 minutes. And within 5 minutes, we should get both end circuit breaker openings. The time of 5 minutes is taken because of circuit breaker auto reclosure issues. And also if the circuit breaker mal operates, then it is to be manually operated within 3 minutes time. Then this is the glance of the code. I don't know if I could go through the technical aspects, but yeah, the outcomes. The outcomes are reduction in alarms from 7,453 to just 34 to 49 line tripping alarms. So we filtered out the data set and we just got 34 to 49 line tripping alarms, which were then compared with the actual trippings, actual tripping data which they get. They actually call and confirm if the line has been out from the remote end. So from there, we achieved a similarity of 67.35%. Thus, this shows that the alarm system has improved efficiency and reliability. And we are currently working on that 33% error that we are facing. So these are the references. And thank you. That's all. If there are any questions. Yeah, sure, sir.
Does this kind of filtering not happen in the SCADA system itself?
No, sir. Currently, there is no such logic for SCADA filtering. They actually get alarm data as such from RTUs.
So
And
did you write this for SCADA computer or it is a separate processor?
Sorry, I didn't get you.
Wrote this logic in which platform? A separate computer?
Separate computer. So currently, we are working on a CSV file and we are planning to shift on real-time SCADA.
So would you write this code on the SCADA computer itself as a part of SCADA facility?
Yes, sir. We would integrate with the current electricity grid. Any other questions? Okay. So thank you once again. Thank you for our guides, faculties, and my team members.
Thank you, Khadija. We'll begin with Dr. Shashank Wekhande's session on wide bandgap power devices, GAN, and SIC for power converter in 2-3 minutes.
Check.
Before inviting Dr. Shashank sir, I'd like to give a brief introduction of the person. Dr. Shashank Wekhande received the MS degree in Electrical Engineering from Amravati University, Maharashtra, and PhD degree from the Department of Electrical Engineering, Indian Institute of Technology, Bombay, IIT Bombay that is, in 2001. While working towards the PhD degree, he worked on static wire compensators for applications in active line current conditioning and induction generator control. Subsequently, he worked with Lucent Technologies and Tyco Electronics.
Good morning, guys. Should we start? Wait for some time? Maybe before all the dignitaries join, I would like to just have a one-on-one discussion with you as the students. Uh, Myself, Shashank Wekhande, basically I'm coming from Allegro Microsystems, where we work for power ICs and sensors. primarily into the automotive domain, which is a hardcore hardware related business. In India, what we are seeing is that most of the students are willing to go more and more towards IT. Yes, there was a boom, there was a growth at some point, but slowly, if I'm looking at down the line 10 years, there is equally good opportunities in other domains than hardcore software and IT. If just I'm looking at the electronics as uh, a domain, today we are standing somewhere around 100 billion worth of business. Probably that is going to go to 500 billion. That's a CAGR of about 16 to 18%. Out of that, some of the areas like agriculture electronics, they have a CAGR of about 68, 70%. So I strongly encourage to look other than a core IT fields and then make this whole industry uh, kind of supportive with good students, brilliant students like you, and that's what I would encourage. So with that background, let's start for the today's discussion. So this is going to be a disclaimer. This is going to be once again a hardcore electronics, not much into the software. How many people wants to get into this kind of career where you want to make your hands dirty and work on some kind of hardware? How many people are willing to work on those? That's great. So primarily I kind of present this whole presentation for students like you. This is going to be my agenda for discussion. We are going to talk about some of the new power electronics devices which are coming up, and these will be more popular in next 8 to 10 years. That's what we expect. So traditional devices like diode, transistors, well, good, you have studied. I would like to discuss some of the new generation devices which are coming up and which are getting more popular into the high power, high frequency, compact power electronics devices. So that's one of my objective, to introduce you to the newer devices. And second, to introduce some of the new topologies specifically used for high power, high frequency DC-DC converters to start with. So phase shifted bridge converters, LLC resonant or dual active bridges normally used for all these EV applications. We will just touch base upon some of these topologies and applications. So primarily today we use three mainly devices. Of course MOSFETs are there, but I am looking little more than MOSFETs. Those are IGBTs, silicon carbide and gallium nitride devices. Let's take a look at one by one. Got stuck somewhere, I guess. Can someone help? Okay, sorry. So move right. Move left. Sorry. So IGBT stands for insulated gate bipolar transistor. It's kind of a MOSFET input transistor output type of device, and that combines the goodies of both. Transistor family has some of the advantages, MOSFET has some of the advantages such as driving ease, uh, majority current carriers, and that helps to get into the MOSFET region. Transistor has low offset and it's cheaper. So IGBT was the first device which kind of integrates the goodies of both families, MOSFET family and transistor, and come up like IGBT. Usually they are rated more than 600 volt, 800 volts. So the sweet spot for these devices starts at least at 600 volts, and then if you are looking at frequency less than 100 kilohertz. If you are looking for higher frequencies, once again MOSFETs or GaN or wide band gap devices are better, or if you are looking for voltages less than say 200 volt, MOSFETs are a option for appropriate option for those applications. So main advantages of IGBT over power MOSFET and BJT are they have low turn on. So low turn on voltage means lower losses, because the loss across device is nothing but the voltage drop across the device into the current. If you have lesser drop, naturally lower power drop. Lesser power means higher efficiency, higher mileage for your vehicles, better utilization of batteries, or in general electrical energy available all around. Also the better efficiency or lower power loss also provides you a better thermal, because now you are not converting that losses into heat and you don't have to manage that heat. So it makes all design more efficient. Lower driving power because of the MOSFET type of structure. Now you don't have to pass the current like in transistor. So the driving becomes easy. You just apply a say probably 10 to 15 volt signal and MOSFET turns on, and 0 to turn it off the device. So simpler device to control. So probably you are well familiar with IGBTs. This is how the temperature graph looks like. So why IGBTs are preferred? One, it has a positive tempo. So positive tempo means when you are doing the paralleling of devices, or within the device also, we don't put a single MOSFET as a single MOSFET. They will be like multiple devices on one die parallel together. So when a lot of current flows, there could be a hotspot because of the negative uh, temperature characteristics like in transistors or minority carriers. So over here what happens that when you put multiple devices in parallel, if one starts taking more current, its forward voltage increases, power loss increases, so the temperature increases, and eventually the current balances out between the devices. So that's why this positive tempo is important parameter when you are looking for a power electronics device. I think let me skip this one. Let's jump to these newer devices, the wide bandgap semiconductor. Why we call as a wide bandgap? Basically, if you have studied into the physics, we have this valence band and free band, where in the valence band is the number of electrons in the outer orbit, but those are not free, they cannot contribute to the current. If you give little bit energy to those electrons, these electrons escape, they get into the conduction band. Once they get into the conduction band, you have lot of electrons to carry the current, and that's why that's how the device turns on, where you have plenty of electrons. So in wide band gap, the gap between the outer orbit and or the valence band and the conduction band is reasonably higher, and so one need to provide lot more energy in order to excite these electrons and get into the conduction. This allows you to have high voltage devices, because applying little bit higher voltage or applying little bit of temperature cannot provide enough energy for this valence electron to come out of this orbit and get into the conduction. So the leakage current is smaller for the devices, and they can handle much higher voltages with a smaller die area. So smaller die area for semiconductor manufacturer means lesser cost, and so overall package becomes simpler, cost becomes simpler, and the overall capacitances, parasitics, everything comes down, and it helps us to build the more high frequency, high power devices. So that's why the reason why wide band gaps are becoming popular. As on today, commercially, silicon carbide and gallium nitride, these are the two devices or the two families are becoming popular. This is not the end of the what I can say wide band gap devices. There are gallium arsenide and many others which are popping up. But if you ask commercially what is available and what's economically viable for next probably 8 to 10 years, then these are the two product families which are going to be what you will be using in high power, high frequency application. If you look at the typical band gap, germanium, the very first devices were invented on germanium. Then they moved, because there was a lot of leakage current on germanium, they moved to silicon. Silicon has about 1.1 of band gap area, whereas now the newer devices, they are 3 times more band gap, or they need 3 times more band gap energy, meaning by they can handle at least 3 times more breakdown voltage in the same package. So which allows you to make the devices smaller and allow you to work at the higher voltage. So first one, the most important, silicon carbide. So silicon carbide MOSFETs are very similar as far as the construction is concerned to our standard silicon type of MOSFETs. The only difference is probably the material being used over there. We use standard silicon over here, we use a silicon carbide over here, which allows us to have a narrower drift region. So the way MOSFETs are built, on a substrate. I don't know, once again, you are from the VLSI background or are you going into those courses, but usually the device is fabricated such that you have an ingot, a plain, what you can say, doped silicon material, and over there you start doping in order to create the N region or the P region. So when I say N plus substrate, that means that it's heavily doped, and when I say just N or N minus, these are slightly lowerly doped areas. So this heavily doped material, and then this is the actual region where your current will start flowing. So one is the source, another is the gate, and when you apply some voltage to the gate, this particular channel which was initially off, no free electrons available over there, when a positive voltage is applied, lot of electrons starts coming up in this region from this lightly doped material, and the channel becomes on. I'm sorry. I'm still not. Something is wrong with this one. Can you check properly? I'm not very sure. So the driving characteristics or the input characteristics of silicon carbide is very similar to that of a standard MOS. These devices are the SICs, they are normally better above 800 volt and above, and frequency range probably 300 to 400 kilohertz. If you are looking something at 1 megahertz, you must have seen these 65 watt adapters nowadays, mobile chargers. They are really small. They nowadays tell you also that these are GaN type of drivers, which makes that very high density, and you are able to put that 65 watt DC-DC converter in such a small 1 cubic inch form factor, which it used to take, like, if probably if you are looking 5 years back, your mobile adapter was like this brick, and now the same brick is now at least 4 to 5 times smaller, just because of high frequency switching. In older days, when we were working with MOSFET, say 800 volt MOSFET, we were not able to switch more than 20 kilohertz, that's it, 20-25 kilohertz. With these kind of devices, we are able to switch 100 kilohertz or at least 300 kilohertz. Once you go for the higher frequency, you can reduce the inductor, you can reduce the capacitor, you can reduce the filter size, you can make overall board compact, and thereby minimize the overall size and cost of the device. So that's all advantages which these high frequency devices bring to the table. So I will talk more on this one, the construction, but primarily there are two types of GaN devices when you get into the market for looking for these devices. One is enhancement and another is depletion. So enhancement is like normally turned off, and the channel enhances or the device turns on when you apply a voltage to the device, whereas the depletion type of devices normally will remain on and they will deplete when you give a control command to it, like a gate voltage. So when the gate voltage is not there, in absence of gate voltage, enhancement mode device will remain off, whereas the depletion mode device will remain on. Usually this is not a good situation, that without giving any command the device remains on. That is not something you would like to do. So commercially these depletion type of devices are not used. Even though the technology exists, we don't use them commercially, because you don't want something to be on when you don't want. Say for example, in your car, if you don't put your key and your car starts, then that's not the good feature. So same analogy over here. If you are not giving the gate signal, the device should remain off. So to do that one, people use additional circuitry, something similar to IGBTs, what we call as a cascade structure, and with that cascade structure, these devices also are made normally off, and still they are called as a depletion type of devices. So when I am looking at a depletion device which inherently should be on, but forcefully by adding some additional components, we are making it that it remains off when the gate command is not there. One of the advantage of these enhancement GaN is, or even for that matter depletion GaNs also, is that there is no body diode. So when you use a MOSFET, always there will be body diode, and that inherently will be there because of the construction of the device. So you won't get a single MOSFET without parasitic diode. So if you say that I want a MOSFET which should have the blocking capacity on both the directions, no, such device doesn't exist. You will always get a diode, and if you want to create such kind of device, you have to put two back-to-back MOSFETs and create another MOSFET. But primarily when you are looking at a MOSFET, always it will have a body diode. When it's a body diode, there will be always a reverse recovery associated with it, and the reverse recovery is very difficult to manage. It results into the losses, it results into uncontrolled losses, and that's why people use either Schottky or some other type of devices. But in general, body diodes sometimes are good depending upon what kind of application you have, but in general they result into significant reverse recovery losses and are not preferred. So both these GaN devices, they allow you to, I mean, they don't have the body diode, and that allows you to have lesser losses in the reverse recovery and thus getting the better efficiency. So other than high voltage, better conductivity, high frequency, one of the advantage of this is that there is no reverse recovery losses because associated to the diode. Let's take a look at the depletion devices, because enhancements are simpler, like standard MOSFET. You apply the voltage, device turns off, you remove the voltage, device turns off. But in case of depletion type of device, like this is the GaN. So this GaN is put either in series with a small MOSFET, which can carry the same amount of current, but it doesn't have to hold the full voltage now. Say if I am applying 0 to 5 volt over here, then at the most on the drain of this MOSFET, I am going to get only 5 volt, because the moment this node starts going above 5 volt, this GaN FET will try to turn off and eventually the voltage will be controlled over there. So I need to develop only a MOSFET here which can carry full amount of current, but rated only for 5 volt, which can be developed and designed as a much cheaper device than a full blown 600 volt MOSFET. So the GaNs help me over here, that the 600 volt will be managed by the GaN part, but the input section is not good for the GaN, it's always on. So in order to enable or disable, we use one more channel or one more MOSFET in series with, and this type of construction is called as a cascode, where two devices are put into series and the gate signals are controlled. So this is the typical structure TI has, but you need two different signals. Some of the suppliers, they provide a single device where the GaN's gate is connected to the source node itself, so that whenever this device turns off, you automatically get a negative voltage on the gate of the GaN, and the GaN also turns off. So that's how the GaNs are managed in these configurations. Advantage of having this, okay, let me get on to the next slide and I will talk about that one. So we looked at how the enhancements are made, the depletions are designed. In case of enhancement, what you do have is so there will, the structure is like this. You are growing the wafer or the die vertically. Once again, there is a substrate, either N plus. Then somewhere in between we have this GaN layer, and this GaN layer, when it is doped with the aluminum, it creates something what we call as a 2D gas, the two-dimensional electron gas. So means there are plenty of electrons available. So to start with, lot of electrons are being pulled from the aluminum, and these are available in your GaN layer channel, and because free electrons are readily available without any gate voltage, the channel is normally on. So over here a small p type is doped. That's the difference they do compared to the depletion mode, that in depletion mode there is no p type, thereby the electrons are free over here. In this layer we add a small p type which kind of keeps the electron and holes together, thereby the channel remains electron free and it's normally off. Problem with enhancement devices is that the threshold is very little. So even we are forcefully pulling it. So we are just trying to create one PN junction over here, and thereby we are trying to extract all the electrons which are available into this gas or 2D gas, 2D electron, free electrons over there by a P layer. So the potential difference is only 0.7 volt, and I just need 1 volt to turn on once again. So if you apply 1 volt to the gate, the device once again will turn on for these type of devices. When you are looking for the high power applications, high frequency application, in most of the application, 1 volt gate is not enough. That can come because of the very spurious things, noise, ground bounce, the difference between the power ground and signal ground, and so many things. So that doesn't allow you to have a reliable device just at 1 volt. So these devices, the enhancement devices, are normally used for high frequency but low power application, like a compact USB chargers, but these cannot be used for the high power applications where, like automotive, where lot of reliability is at stake. Over there, probably you would go with the depletion mode, because for the depletion mode, your front end is a MOSFET which is a 20 volt rated, as well as it can need, or it needs at least 4 or 5 volt, which makes the system much more noise immune. So in general, the comparison between the multiple devices, what is good, what is bad, one can get a very good idea from this screenshot that which device should be used for what kind of application. So we are comparing primarily available MOSFETs, silicon based, which is a MOSFET, and then IGBT, silicon carbide, and GaNs. So GaNs are good when you want to go for the high frequency application, but reasonably or somewhat lower voltages, whereas silicon carbides are good for the higher breakdown voltage as well as for higher conductivity and moderate speeds as compared to GaN. So this can have much faster, like up to 10 megahertz type of switching frequency it can switch, whereas they can be good up to 1 megahertz. So even though these are theoretical numbers, in the real life you may be using it somewhere like 1/3 to 1/4 of the frequency which is they are rated for. I'll give you some examples because this is all theoretical discussions we have. How do I select and how do I read a data sheet? Because all these are new devices, you need to understand how to read the data sheet. Reading the data sheet of the semiconductor company is the most important thing as a power electronics or in general any electronics designer. We as a semiconductor manufacturers, we put lot of information over there, but the user need to understand in your context and your application that what it means to you. So as an example, when I say a absolute maximum specification, these devices can handle this much trace only. So particularly this TP658015 device is rated for 650 volt VDS, meaning by it can handle 650 millivolts. So if you have applications say 400 volt or 3-phase bridge, which can go up to say 500 volt, 550 volt, this is barely good enough device. You may need a 800 volt, but probably this is suitable. Look at the voltage rating. The gate voltage can take about 20 volt plus minus, and the gate threshold, which is the voltage or the minimum voltage required at least to turn on the FET, which is around somewhere around 4 volts. So it tells you that up to 4 volt this device is ensured to remain off, and even if the noise comes, say 1 or 2 volts of noise here and there, this device is not going to turn on. But have you gone through devices and physics? Do you study these type of things? Yes. Okay, good. So when you are looking at the MOSFET, we will have 3 capacitances, one gate to source capacitance, gate to drain capacitance, and drain to source capacitance. All these are parasitics, and as much as possible you want to have these capacitances smaller, because all these are parasitics and they may result into the losses if not handled properly. So for depletion type of GaN, just remember these numbers, and we will, when it comes to the enhancement, I will show the comparison between these 2 devices and how do you pick up the device. 5000 puff, 300 puff, 26 puff, and somewhere the total gate charge is about 74 coulomb. So some good things, some bad things. Gate threshold is higher, but the capacitances and nanocoulombs also are significantly higher. When I am looking at a similar device in enhancement mode, now look at these numbers. The VGS threshold, which used to be 4 volt, now is only 1.7 volt, and the minimum is only 1.2 volt, that too at 25 degrees C. At hot, these numbers will come down. So it is possible that even if you have a noise of 1 volt, this device may turn on and may cause malfunction, may cause short circuit, may cause damages to the circuit, and extreme care should be taken in order to handle these type of devices because thresholds are very small. So not many people like that particular part. But on the other side, look at the charge. 6.2 nanocoulomb as compared to 72 nanocoulomb. Capacitors 225 puff as compared to 5000 puff over there for the depletion type of devices. So it makes a lot of advantage for enhancement when I'm looking at the parasitics and other things. So that's all good. So if you, whenever you want to design, just don't go by GAN. Oh, I'm using a GAN. You had to select the right device, you had to select the right technology in order to suit your application. And looking at your application and what you need, you select the right part and right specifications required for that. So I just wanted to highlight some of the examples that what makes these two technologies different and where you should be going for what kind of device. Coming back on our previous depletion type of things, some of the advantages thing, positive tempo, as the temperature goes up, RDS on goes up, as we discussed in earlier, it helps me to do the paralleling of the devices, they share the power and all those things. So this is somewhat similar to the MOSFET. When I'm going for the enhancement, still very much same, I get a positive temperature coefficient and there is no much difference between these two. But the main difference comes up at VGS. Look at this VGS, the VGS just at 1 volt the device is able to turn on, and that's not something you would like to. At the Allegro we make a lot of gate drivers and some of the small gate driver. So GAN gate drivers are really tiny. Sorry. No? Okay, fine. Whenever you are doing the high power, isolated, multi-layer type of DC-DC converters, you need the gate driver which can handle rated voltage, deliver required gate power, and when I am doing the isolated power, you always need some power on the primary side to process on the low level side. Also you need the isolated side because particularly for this bootstrap type device, this is sitting at 600 volt. Now when this turns on, the source node also will go to 600 volt, and so the gate voltage needs to float above that one. So we need an isolated power supply in order to handle this one. There are other reasons also why you want to have the isolation between the power stage and low power analog and digital section. We will talk some other time, I think this is not the topic. Point is that you need a primary power supply, secondary power supply, and Allegro integrates a transformer, coil, everything, and put into a small 10 by 7.7 package and provides the industry's smallest, most efficient gate driver, and that's what my company is. So as we saw, the requirements for GAN and requirements for silicon carbide are different. So we have different drivers for silicon carbide as well as for GAN devices. Also within GAN devices, depending upon either you are going for a enhancement type or depletion type. So if you are going for depletion type, you must apply negative voltage because we saw that the gate threshold is very small, 1 volt only. So even if I apply little bit voltage, the device can turn on. So you need to put this gate normally at the negative level, something like a -3, -4 volt. That gives you enough safety so that the device doesn't turn on spuriously. So when you are looking at the enhancement type of devices, usually the bipolar supply is applied, negative and positive voltage, whereas you are going for cascode type or the depletion type of GAN devices, usually a single 8 to 10 volt voltage is enough to drive those FETs. So all these are covered with these 3 or 4 device product family. So this is mainly for our silicon carbide device. Everything is packaged into a small package. Protections, primary and secondary, driving circuitry, and power, what we call as a power through technology. With that one, I have finished my discussion about the devices. I would like to touch base upon some of the DC-DC converter topologies being used in high power applications. So before we switch our gears, are there any questions? Please, sir.
All these devices which you mentioned, gallium nitride and silicon carbide and all. So as a country, are we still relying on the imported stuff, or like people like CDIL or GATEC or somebody, SCL is making something in-house?
We are all 100% relying on external. We don't do
So
anything.
there's no foundry in India?
No. We don't.
I heard recently somebody is starting up in I think Surat or Ahmedabad.
So there are 2 or 3 foundries coming up in India.
Right.
Those primarily will be towards digital only.
Not analog.
Very little on analog and almost no on power. When I am saying digital, they are looking at developing microcontrollers, they are trying to develop the network analyzer type of chips. But if I understand correctly, the development of digital design is very simple. It's all VLSI based. You can go over. The process doesn't need, even though you are going like a 20 nanometer, 25 nanometer type of technology, which is, but still it is manageable. And analog and high power is really difficult wafer or foundry process, which as on today, I don't think so that we will have in near future.
So what is the modus operandi? Are we buying only from the off-the-shelf components, or we are designing something and getting it made from some foundry like TSMC or something?
In India,
Okay.
as a user,
As a user.
as a user, you are taking most of the times off the shelf.
Off the shelf.
Yes, sir. We don't get designed anything from TCMC or anybody else.
For the last 20 years, I've been attending seminars in IIT and other places. Like people are working on amp design or gallium nitride, and also where the actual that design is going, whether it is like being fabricated somewhere and then being put.
Yes, absolutely. But TCMC probably is the 80% manufacturer for all these type of things, and at least in near future, I don't think that we are going to have any kind of manufacturing. So overall, manpower ecosystem, and that's why I don't know if you were here or not. When I started my discussion, I was just appealing all the students over here to look beyond IT and software and look for other domains also which are flourishing like anything. And that's may not be today, but if I'm looking at down the line 10 years, VLSI is going to grow. Fabrication is going to grow, components are going to grow, chemicals particularly required for semiconductor, that line is going to grow. So not only the IT and AI, but I think I was just requesting all of these kids to explore little beyond. So as on today, if I want to find out, we are looking for analog designers, and not a single analog designer I am able to find. When it comes to a digital, I will have at least 100 resumes piped up for me.
Analog designers, RF designers are rare breed.
Exactly. So, but if you find one, then it's a gem, and that's kind of the issue what we have in our ecosystem as on today, that we cannot have the fabs in.
My last part of the question is that under this new semiconductor mission policy, NSM policy, whether as an industry, like Allegro being a major player in power electronics, so whether any stake is being put into power electronics, or they are like into digital ICs or some other?
Probably we won't be a part of that mission. Two reasons. One, we are not aligned with the focus. That's what I feel. But we are heavily investing on design. This year we hired about 100 people all in all. We have 2 design centers, one in Pune and one is in Hyderabad. And we will be using the talent pool as on today, but I don't know from manufacturing, Allegro will have any plans. I'm a very small person to comment on that one at this point.
Thank you very much.
Anybody else? Yes, sir. Then, no, his question. Yes, sir.
Depletion mode devices in application is being used.
Yes.
Depletion mode devices.
Yes.
Industry also, they don't prefer.
No, they do prefer. So depletions are good, particularly if you are like looking for the OBD charger, onboard chargers. So I have a big EV, I'm making say 20 kilowatt onboard charger. Now the dead weight is very important over there when I'm looking at the EV type of application. So switching at higher frequencies, making the magnetic smaller, making the filter component smaller is required. And for those type of application, definitely the depletion type are preferred. problem is that higher capacitance, so your driver becomes more expensive. So you have to look from all the sides, right? What is your reliability requirements? So like in adapters, it's all compact, small. Even if it blows, you are not going to make much of a noise out of it. But if your car blows, then it's going to be a major concern for it. So reliability becomes very concerning things over there. And over there, people will be using this depletion type of things where you want to go for the higher frequencies because of the lower parasitics, you will be able to further go up on the higher frequencies and then make the board or converter smaller. So over there, probably I will go with enhancement.
Sir,
Yes, ma'am.
I heard in some paper I read that the FET, they are using for the wide gap this GAN technology FET as compared to MOSFETs.
Yes.
Is it like the two things and it is coming in the industry because MOSFETs are having so many security problems and that the reverse diode technology and all. That's why people are going for this research for FET. Is it replaceable?
FET and MOSFETs are quite similar. Similar topology, similar technology. You have a single channel and they are all majority current carriers and having the advantage of majority current carrier. Being said all that thing, I don't see much from the FET. Reason behind is that if I had to go for the new device and new R&D, I would put money into the silicon carbide or GaN, which allows me to have the wide gap and gap advantage. FETs are essentially silicon based devices only. So the advantage is that I can use the existing wafer process to grow the same FET or the JFET, but if I'm looking at probably down near the line 5 years, FETs are not going to be as competitive as GaN or silicon carbide ones, and at least I feel that in RF, yes, JFETs are still good, but if I'm looking at power applications, probably GaN and silicon carbides will dominate the market.
So GaN and silicon carbide only, but the tool is not MOSFET, but the this FET, field effect capacitor.
No, FET is different to that. FET is a regular silicon-based MOSFET, right? Am I correct?
Yeah, when we are putting the metal oxide with that and giving some security, like
Yes.
we need to put it into so oxidation should not be there, like that. These things are with the MOSFET.
Right. So I think your question was the
FET
will
is having
FET
any
will see
future for
any
this
future in
GaN technology only.
over GaN, right?
Yeah,
And that's what the perspective I was trying to give you, that probably not. Most likely because of the wide band gap structure of these devices, they may get more positive.
I'm so sorry.
Maybe we'll discuss. I'm not able to.
No, no. My question is that it's a wide gap only. Wide gap technology, gallium, gallium nitride and SiC,
Yes.
silicon carbide. This
Yes.
technology only,
Yes.
in spite of manufacturing MOSFET, what you have given.
Yes.
I have read in one paper that the FETs are also, they are manufacturing for this wide gap technology only. So this is any future in this technology. That's all.
I'm not getting. Maybe we'll discuss.
Fine. No, thank you.
So So you must be familiar. So you must be familiar with standard buck, boost, those type of topologies in power electronics, which are non-isolated and typically used say sub 1 kilowatt type of application. When we are looking at high power going from say 5 kilowatt, 10 kilowatt, particularly for the EV type of application, that's the most emerging market, and why I am repeatedly getting into the EV discussion is that that's the most emerging market as on today what we see, and most of the power electronics research is happening on that particular application. And then you have very high power like in a transmission which goes into the megavolts and megawatt type of application. Once again, that's not my domain of discussion. So when I'm looking at these medium power applications, somewhere say 10 kilowatt to 100 kilowatt type of application, we are going to discuss about some of the topologies used in these ones. So the most basic simple topology is phase shifted bridge. So traditional bridge converter had 4 MOSFETs, 1, 2, 3, 4, overall traditional. They were controlled such that these two FETs will remain on in one cycle, these two FETs will remain on in another cycle. By controlling the duty cycle of these devices, you will control the power or the energy getting transferred from primary to secondary or vice versa for the bidirectional ones. So that's how these usual traditional full bridge converters used to work, and then there were derivatives of that. You can have a half bridge or you can have a semi half bridge and so on, but those were the PWM based DC-DC converter, where you will control the PWM duty cycle for these devices and control the power transfer or the energy transfer. In case of phase shifted converters, still these two are operated in 180-degree phase shift. When QA is on, QB remains off, and vice versa. If they turn on both together, then definitely there will be shoot through, and that's what we will not like it. So these two are turned on with 180-degree phase shift, but the phase shift between this leg and this leg is controlled, so that whenever the or during the instance when this FET is on and this FET is on, only during that period the energy will be transferred. For rest of the period, the energy will be just circulating between the magnetizing inductance and the devices over here in the primary, and by controlling the phase shift between these devices, you will transfer the energy. So that's basically the idea behind this. Why these are becoming more popular? These are becoming popular because it allows you to go for the zero voltage switching. So if you know the losses in the device, we have two types of losses. One is the conduction loss, one is the switching loss. These are the broadly classified losses in one device. So conduction loss, when the device is on, its resistance or its voltage drop into current is the drop across the device, and that's by conduction loss. Switching loss, whenever the device is turning on or device is turning off, there are some losses associated with the on and off process, and that's what we call as a switching loss. So if theoretically, uh, if you can turn on this device when the voltage across this device was 0, the product of voltage into current, because voltage is 0, will be 0, and so the power loss will be 0. So there are two product families, what we call as the 0 voltage and 0 current resonance. Most of the people will be going, or majority of people will be going for ZVS type of technologies, 0 voltage switching, because they are easy to implement. And one of the advantage of this full bridge phase shifted converter is that it allows you to switch with 0 voltage and reduce the switching losses. How do they operate? So as I discussed, QA and QB are switched at 50% duty cycle and 180-degree out of phase for each. The PWM for QC and QD are phase shifted with reference to this one. You can still do the PWMing, but you can apply the phase shifting also if you want in parallel. And then the energy is transferred. When these two devices are on, then you see some voltage across the primary of the transformer, secondary voltage is generated, and so the energy is transferred from between primary and secondary. When these two devices are on, the magnetizing energy is circulating between these two devices, or if the bottom devices are on, your magnetizing energy will be circulating between the top side leg or bottom side leg, and depending upon the active time period to freewheeling period, the net energy transferred between from primary to secondary can be controlled. Graphically some waveforms. So you can see that QA and QB, they are switched 180-degree phase shifted, but whenever the phase shift between the A MOSFET and C MOSFET, this can be controlled. So when they overlap or when you have a narrower duty cycle, lesser energy will be transferred. When the phase shift is increased, you get more voltage across the transformer, and then the more output voltage can be generated with this one, and that's how the higher power is transferred from primary to secondary. So in a nutshell, by controlling the phase shift between the two legs, the power is transferred over here, and inherently a ZVS operation is achieved, whereby the better switching frequency losses can be achieved. I strongly suggest you guys to do the simulations. no matter what you do. It always give you a lot of good insight into the circuit. So I'm just showing one example. I'm showing one example using LT-Spice over here, but a lot of time it happens that at least at student level it becomes very difficult for you to build the boards, assemble, test it. But there are so good simulators available nowadays that it gives a good replica of what finally you would have got. So I strongly encourage you to use the simulators. It could be the simulators for polytronics, it could be simulators for microcontroller, Arduino, Raspberry Pi, for all kind of things. You don't have to have the full hardware set with you. You can still play with the software on your computer itself and get lot more insights over there and ask the questions. Say particularly in this type of things, right? What is happening over here? Why this current is slowly damping over here? On the rising side, I'm getting current like this. Falling side, I'm getting this current like this. Think about these, increase your thought process. That's going to give you, don't be bookish. A lot of things will be there in the book, but the book is not going to teach you each and everything. I think ultimately you have to stand on your feet and then you have to understand, and the simulators help you to give a lot of insights. What all we study in books probably is very idealistic. When you come to the industry, when you build your own circuit, world is quite different and the issues are different. It's not the simple as, okay, turn on the devices, I'm getting the power. It's a stability, it's a losses, it's a thermal management, and so on and so forth. So to give those kind of insights, definitely these simulators help you, and I strongly encourage to use, and that's why I just pulled this slide to show how am I simulating one of the phase shifted bridge converter and what kind of results you can get over here. What do you mean by, so we speak about ZVS, so I just wanted to give how the ZVS actually comes into picture. Take a classic example of synchronous buck converter where I have a top side MOSFET and bottom side MOSFET, which is called as a one totem pole. So when this device turns on, the energy is transferred from input to output. When this device QA turns off and QB turns on, the energy just free will. So same thing as that of any half bridge or full bridge, except that this is now a non-isolated topology. So working principle wise, both are same. By controlling the duty cycle, you are controlling the output power. In a traditional way, when once again, probably when you look at the books, nobody is going to tell you, but over here, you need to have some kind of dead time between the two devices. You cannot operate with a 50% duty cycle. Otherwise, any small mismatch between the delays, you are going to have a lot of current to these MOSFETs and they will damage. So you put some dead time between these two, and when you have a dead time, you will see this kind of small notch over here, which is the indication of a diode conduction. Over there, the current is freewheeling through the diode. So this, when the MOSFET is on, current is flowing through this inductor, polarity of inductor is like this, voltage polarity, this is plus, this is minus. When this turns off, for short time, you don't turn on the second guy at all. And this inductor current is not going to find the path through the body diode of the bottom FET. What that does is that now this channel or the current is flowing through the diode, and it's not putting the full voltage at this node, but it is just a 0.7 volt or a diode drop over there. So when the channel part turns on, it will see only 0.7 volt across it, and the switching loss across that one will be reasonably smaller. So all that output parasitic capacitor or the, of course, I'm just once again giving some idea without considering the reverse recovery losses of the diode, but when I'm looking at the ZVS only, this will recover all the losses from the COSS as well as the diode and allow you to have the much better losses over there. Professor, with your permission. So this is invariably we are getting the zero voltage switching, particularly for the bottom MOSFET. So when I'm looking at the operation of a synchronous buck converter in CCM mode, continuous conduction mode, you can always get a bottom device switching at zero voltage. Probably top side will be hard switch, but you can minimize the losses in this device. So the same principle was there for the phase shifted bridge converter, whereby by controlling the phase shift between these two devices, the currents first made to flow this body diode and parasitic capacitances and turned on when during the dead time when the voltage across them was very small or almost 0.7 volt, allowing you to have the zero voltage switching for this kind of converter and get better switching efficiency. Another popular high power converter topology is this dual active bridge converter, or small as a DAP. What is that dual active bridge? Here, instead of having the rectifier on the secondary side, you will also have active bridge on the secondary side. Thereby, invariably, energy can be transferred back and forth between the two sources. This is classical example once again in EV, where we are putting a regenerative battery and the inverter type of application. Of course, that will be a three phase. I am just showing us a simplified thing. So, if you are looking at, say, uh, main battery charging from the EV, or there are 48 volt to 12 volt two double systems, and energy goes back and forth between 48 volt and 12 volt batteries. For those type of systems, you can have a DAP converters, which allows you to have the bidirectional power transfer between primary to secondary. Typical application, as I said, battery chargers, energy storage, EVs, 48 volt DC-DC converters. The key features are over here is that now we are controlling still through phase shift, but the phase shift is controlled between the primary and secondary bridges, and by controlling the phase shift between primary and secondary bridge, the bidirectional power flow is achieved. Power density, particularly for this type of application, will be high because of the we can operate at higher frequencies. They can still operate with a zero voltage. You have isolated operation just because there is a transformer, and usually this results into better efficiency. In general, whenever you have two fundamentals, sinusoidal, so when you have two sinusoidal power supplies separated by some kind of inductor, the energy can be transferred between, for the same amplitude, from the source 1 to source 2, if this source is leading or lagging. So, by controlling the phase shift between the two sources, you can control the power getting transferred from VL1 to VL2 or vice versa. So, the equation, particularly for the sinusoidal ones, that's normally used in the power systems, that power delivery will be V1 V2 sin theta by omega L, where theta is the angle between the phase shift between the two converters. Now, when you are looking at the DC-DC converter, it may not be possible to generate the sinusoidal waveform. It's a lot easier to just generate square waves. So, we deal with the square waves, and here in the dual active bridge, still the MOSFETs are turned on and off, not the sinusoidal. You will have some fundamental component and some switching components out of that one, but in general the principle still remain the same. By controlling the phase shift between this bridge and this bridge, effectively you have one voltage source, you have another voltage source, and controlling the phase shift between these two applies a resultant voltage across this transformer, which allows you to have the bidirectional energy transfer. Sorry, I am just running little faster to limit within the time, but if you have any questions, we will have some ample time after the discussion. So, that was the equation when I am looking at the sinusoidal ones. If I have a square wave, probably the power transfer between these two is governed by this formula, or if you want to know how to calculate the theta for required power transfer, equation used normally is this one. Probably Savan sir uses LLC converters very extensively on his some of these applications. I think you did your masters and PhD also on these type of converters, right? So, LLC converters gives you one more advantage. So, reason is that the zero voltage switching has certain limitation. You cannot get the zero voltage switching over very wide range of applications, and then LC resonant converter comes into picture, where you have a square wave. Essentially there are many resonant circuit topology is available. If you open any IEEE journal or any IEEE conference book, you will find many papers over there. The basics still remain the same. You switch the devices, you generate the square wave, you feed that square wave to some resonant tank circuit, and then derive the power by controlling most of the times by the frequency. So, you sweep the frequency, and as you go towards the resonant frequency, more of energy transferred would be there, and vice versa. You can have a simple LC type of first order LC type of devices. The problem with these LC, only single C type of converters, is that these are very load dependent. So if you have enough current, zero voltage switching or zero current switching can be achieved. But as you go for the lighter loads or lower loads, achieving the zero voltage switching may not be possible. So over there we add one more component, which is called as the LLC or LCC type of converter. So two inductors, one capacitor, or two capacitors, one inductor. These are more industry standard configurations, and as I was discussing, there are a number of different configurations and converter topologies are available. We are going to focus primarily on LLC type of converter. Why LLC? Because over here some of the things are free for me. When I am using isolated transformer, these magnetizing inductance can be part of my transformer and I can minimize some extra inductor over there. The CR could be my resonant parasitics of my MOSFETs and other things lumped together. So CR also can be achieved through the parasitics of MOSFET. Given the specifications of your converter, it may not be always possible that you may completely avoid the CR. You may need some additional CR, but as much as possible people will like to minimize the components and value of components and save the cost. So LLC gives you an advantage over there that some of the parasitics itself can be used as your power component and minimize the overall cost and size of the converter. In general, we know that for any tank circuit, like any LC circuit, our resonant frequency is omega is equal to 1 upon root LC. So from there we know that what is going to be my one sinusoidal period, and that sinusoidal period should be depending on your switching frequency, of course, what frequency you want to achieve, you would like to stick to those frequencies. And based on that, the MOSFETs, usually the capacitance comes as a parasitic capacitance, which is the MOSFET, and you want to discharge those capacitances through the current stored in the inductor during every cycle. So in order to do that one, the energy stored in the inductor must be at least greater than the energy required to discharge that cap. So half Li square and half Cv square, if you equate, you will get the energy that the primary current should be at least equal to Cr by Lr into V in max square. So this equation is nothing but half Li square is equal to half Cv square. You equate them and you will get what is the current required on primary side in order to achieve the zero voltage switching. So now with these kind of things, up to this level only you will be able to achieve the zero voltage switching. Below that it's going to be hard switching, which is normally not the problem, because at lower current anyway the losses are lesser and you don't care much about the losses at some point. This is typical structure for a LLC type of converter. You have a totem pole configuration with two MOSFETs generating the square wave at this node, which is fed to a resonant circuitry, which is LLC isolated by a transformer, and then the diode rectifier. So it essentially has the four blocks: a bridge rectifier, resonant tank, isolation transformer, and a secondary rectifier. Stage 1 generates a square wave either in a full bridge topology or a half bridge topology. Stage 2 feed that square wave to the LLC circuit, which generates the sinusoidal thing. Now depending upon the Q, the LC circuit's Q, and depending upon at what frequency you are operating, the overall gain of the system will change, and by controlling the frequency you can control at what point you would like to operate, and at what point how much power will be transferred will be purely controlled by the operating frequency of this one. So unlike in our standard DC-DC converters where we control the duty cycle, here we control the frequency, operating frequency, and by varying the frequency you will be able to achieve the required power ratio. I think I'm done. Typical waveforms. I think that's it from my side, and any questions, anything I can comment upon? All right then, thank you. Yes, sir.
Do you share any reference designs for the benefit of students to try them out and learn?
We do. Lot of things are there, like the one I was showing, we give them like a reference demo boards. You can request the reference demo boards for the GAN and these ones. We also provide lot of articles, lot of application notes which are there on the web. We provide chips for you to evaluate and test. the boards as well as the devices.
I think you remember there is a Steigerwald's paper.
I'm sorry?
There is a Steigerwald
Yes.
paper,
Mhm.
R. Steigerwald.
Okay.
So he talked about series converter.
Right.
And
Right.
series parallel converter.
Correct.
He didn't mention LLC there.
Correct.
Later on, LLC has become the
Industry
acronym-
terminology.
Acronym has become so popular later on.
Correct.
Industry has adopted like anything. Okay. And
But it's a basically series parallel
it's a series
configuration.
parallel topology. And nowadays, people have developed ASICs
Yes.
just for frequency.
LLC. Yes.
LLC, just
Correct.
for LLC.
Correct.
Like people have developed PFC
Right.
controller.
Right. Right. Right.
Only in ASIC. So likewise, there are in almost every manufacturer. If you take Infineon, if you take Texas Instruments, or
The problem over here mainly is controlling duty cycle is easy. Controlling the frequency which needs a PLL and all the
design
things
is
becomes
always a
difficult.
challenge.
Designing is a
Always,
challenge.
and even if we say that because magnetizing inductance is a design parameter. Okay, here in this case, LFC means the parameter is already decided.
Yes.
Whereas in other topology, we don't bother about whatever is there.
Right.
But while adjusting magnetizing inductance in a transformer, we are increasing leakage.
Yeah, but that's the same case for the flyback converter.
That's the same case.
You put calculated magnetizing inductance. If you have that much magnetic, then only the energy will be transferred, right? It's a very similar over their philosophy. So,
But there is one difference here. Although we are adjusting magnetizing inductance, but I think the energy transfer is taking place unlike flyback.
no, it's not.
Is it similar?
Yeah, very much. It's not flyback.
Yes.
You don't. This is like if you are looking from the control perspective.
Unlike, I am saying unlike flyback converter.
Unlike flyback converter, yeah.
So that way it's not similar to flyback.
No, it's not similar to flyback. The whole topology of LLC is very different, right? You store the energy not only in L, but you store the energy in both L and C only, and that's how you convert it, right? Whereas in flyback converter, you just store the energy into the flyback inductor only.
And then that magnetizing you require some series inductance capacity.
Yes.
So many times the life of those inductance capacitance, the values sometimes change.
So that's why adaptive control and so it puts more pressure onto the control system now. Your controller has to be adaptive enough to understand that how dynamically your LLC values are changing, and then you control your parameters according to that one. So even though you are simplifying on one, so a lot of times we use LR as a leakage inductance. Now if that leakage inductance is not adequate, you put something. But say out of if as an example, if suppose I need 20 nanohenry and I get a 10 nanohenry as a leakage inductance, I just need to put a 10 nanohenry inductor in series with that one. So I cut down some of the cost over there and still utilize my leakage energy there.
Yes, that advantage we have.
Maybe I think we will take that offline.
Any question from we have already implemented in the laboratory.
All right. Thank you very much.
I'd like to invite our principal sir to present a token of gratitude to Dr. Wekhande. Thank you, Dr. Wekhande. That was a really insightful session. Next up, we have a session by Dr. Jason Lai. I'll give you a brief introduction of Dr. Lai. Dr. Lai received the MS and PhD degrees in electrical engineering from the University of Tennessee, Knoxville in 1985 and 1989, respectively. He joined the Electrical Power Research Institute, EPRI, Power Electronics Application Center, Colorado Springs in 1989, where he managed the EPRI-sponsored power electronics research projects, the Oak Ridge National Laboratory in 1993, as the power electronics lead scientist, where he initiated a high power electronics program and developed several novel high power converters, including multi-level converters and soft switching inverters, and the Virginia Polytechnic Institute and State University. Dr. Lai is an IEEE Life Fellow. He received numerous awards, including a Technical Achievement Award in 1995 Lockheed Martin Award and 2016 IEEE Gerald Kleeman Innovation Award. His student teams won grand prizes in 2009 TI Engibus Analog Design Competition and 2011 IEEE International Future Energy Challenge. In 2016 Google Little Box Challenge, his team won top 3 finalists among 2,000 international teams. That is Dr. Jason Lai for you. I'd like to invite our principal sir and Dr. Y.S. Rao to welcome Dr. Jason Lai to our college. Thanks.
Perfect. Okay. Thank you. How do I order? Okay. Thank you very much. This is my honor to be here. I'm on a USA State of Department, the Department of State mission on a Fulbright specialist, visiting VNIT in Nagpur. Just happened to be here for this wonderful opportunity to talk to everybody. So my talk today is related to the high power. In the future, you are going to see a lot of power electronics going into utilities. And my topic is started with the electrification first. That's okay. So I'll start with electrification, the age of electrification. Then we move on to other power electronics.
Towards the left.
Toward left. Oh, okay. So I'll go through some medium voltage power electronics, and introduce a new type of multi-level inverter we call cascaded, binary cascaded multi-level inverter. And then I'll show you the design challenges, how to achieve this high voltage, high power electronics. Okay, and then make a conclusion. Okay, so let me start with a question for you. Okay, The question is, what is the greatest invention in the world in the last century, in the 20th century? Think about it. You probably can never get it right. Okay. Ooh. Oh, sorry. So here. Okay. So, is it TV? No, right? How about a computer? No. You would think computer is a great invention. What about internet? No. So, mobile phone? So it's not. So finally, this one, electrification. You never thought of it. That's the greatest invention in the last century. Okay, so that's the topic I want to start with. Why is the electrification? Okay, without electrification, all these are useless, right? Okay, so electrification start with when? In 140 years ago, with a DC machine. That was designed by Thomas Edison, so you know that. You know him very well. He designed 25 kilowatt generator. At that time, they called DC dynamo. And he delivered the power to New York City. Okay, that is the start of electrification. And that's a DC machine. Everybody knows we have a brush. And then if you learn the electric machine in the electrical engineering, you've probably seen this kind of picture. Okay, so that brush is the problem. I have to maintain it, and perhaps every month, otherwise the brush wear out. But the worst scenario is when it's sent to New York City, at the end of the street, the light is so dim that people complain. And that time we have no way to increase the voltage, and that control of the DC power at that time, it's impossible to increase, but you can reduce, but not possible to increase. So that's long distance transmission becomes the issue. So then someone you probably know very well, AC dynamo. Who invented the AC dynamo? Tesla, right? Yeah, Nikola Tesla. Is that? Not familiar with this. So in 1888, he invented the AC dynamo. At that time, they called dynamo. They didn't call AC generator or AC machine. So initially, he started with a two-phase, then converted to three-phase. Today, we're seeing three-phase, but initial design was a two-phase, and it's rotating with a constant field. The field magnitude is constant, but his design is with the stator and the rotor configuration. So you can rotate the field. That is something we never imagined. So now, with the Nikola Tesla, it's still not enough. Okay, why? The electrification requires a transmission of the power, right? So who did it? George Washington, George Westinghouse. Sorry, George Westinghouse is a business person, but is also a very good engineer. So he started with a transformer design and hook up with an AC dynamo, and in the end, he can transmit very long distance and power the houses very well. So that transformer is commercialized, and then the entire system today is what we see. Without Westinghouse and Nikola Tesla, we don't see this electrification. It's AC electrification. So that is today's scenario. So electrified power system in today is like this. You have a power plant, and then, the power plant goes through high voltage, that's a step up transformer, and then very, very high voltage, and then after a long distance, then you drop the voltage, but that is still thousands of, tens of thousand volts. It's just too dangerous. Yeah, we cannot use it. So in the end, we drop the voltage down to 110, 220. In US, it's 110. In India, it's 220. And then through that, we have a lot of big transformers. And so that's today's scenario for electrification. Okay, so let's move on. So you remember there's a movie called Current War, right? And that is describing the fighting between AC and DC. And in the end, AC won. Okay, so let's move on. That AC system today is having a challenge from electronics, because everything today is electronics. Let's look at the electronic evolution. We started with 1930, the invention of rectifying diode, and then in 1947, there's a first transistor was invented. That was a JFET, junction field effect transistor. Then later is a bipolar junction transistor. Then the that's okay. In 1958, it's IC invented that, and then in later is a metal oxide semiconductor field effect transistor, MOSFET today. Then, let me see, why? Yeah, so all the devices that's making the electronics possible. Now, power electronics is on top of electronics. So what is power electronics? How did power electronics evolve? First, 1956, there's a thyristor called silicon control rectifier. Okay, that can process the high power. And then GTO is a gate turn off thyristor, because SCR you can turn on, but you cannot turn off. So later there's a GTO. Then later MOSFET becomes bigger. So initially MOSFET is like a planar device, and now it becomes vertical. So you can use a very large chip to make a power MOSFET. And then power MOSFET has an issue with body diode. So there's a new type of invention called IGBT. IGBT is a kind of bipolar, but the gating is a MOSFET type. So it's very efficient and no body diode. So it dominates for the last 30, 40 years until wide bandgap semiconductor devices, silicon carbide and gallium nitride. Okay, so you can see the power electronics and the electronics, they come together, and that is about to change the electrification very soon. Okay, and that is the topic I want to move on. The first look at the system. When it was AC, you cannot process the power from the renewable energy, such that the photovoltaic, the wind power, they all require, oh, I cannot touch that. they all require DC in the middle, the DC. And if I have the photovoltaic want to tie to AC, I need an inverter, and that inverter is the power electronics. So you need a power electronics now. Wind is the same. I convert the rotating output, which is AC, but I don't tie that AC to the grid because that AC is a variable frequency, variable magnitude. So you put a DC in the middle to regulate it. So that new age, that the source is no longer traditional rotation machine, not the coal-fired plant anymore. Our feature source is all from renewable. And that renewable requires power electronics to process. Okay, so the new era is coming. And then the problem with a traditional low frequency transformer also, we found that the weight. I have a 750 kVA transformer. The weight is 5,000 kilograms. If I use electronics to make a transformer, the solid-state transformer, you probably easily cut 1 0. No, you can even cut further. You can even cut further. It's probably no more than 100 kilograms. Yeah. So I'll show you 100 kVA design we have. It's basically portable. Not like this. Okay, so that's the issue. Very bulky, very lossy, and environmental unfriendly. The oil, they require mineral oil, and in the summer, they can explode it. So very dangerous. Okay, and then there's no regulation at all. You cannot change the voltage. When the load drops the voltage, you cannot change it. No regulation. So not like electronics, we can regulate. And there's no protection for traditional transformer. And no communication. Okay, really, really bad news for traditional transformer. Okay, so in the end, it's even worse. Your transformer can only deal with AC, but our load, not just the source, our loads are mostly DC. You look at your gadget, your cell phone, your computer, your monitor, your everything, except the air conditioning. But even air conditioning is DC source now. Because I want to adjust the speed, I have to use a DC source. So in your house, really don't see any DC load except, well, in the US, we cook with a stove. But in India, most of you use natural gas. So still, so you look at it, the load is probably no longer AC load everywhere. So the source is DC or require DC power processing. The load is DC, so why do we use AC transmission system? So that high voltage DC transmission system is coming up. You can get almost the same voltage level, but today I start with a medium voltage because medium voltage we can deal even in the university. Not the industry. In industry, you can deal with a very, very large scale. But at university, we can deal with a medium voltage level today. Okay, so the medium voltage, let's understand what is medium voltage first. In the commercial building in the US, we have 4.16 kV. That is line to line. Then line to neutral is only 2.4 kV. Now we start with that. I didn't see any voltage lower than that. But in general definition, when your voltage is beyond 1 kV, we already consider medium voltage. Yeah. And then in US, the power system, medium voltage, the most popular voltage is called 15 kV class, and that is almost 99% of the entire distribution system. 15 kV class. I've seen 11 kV in India, and then I see most of US is 13.2, 13.8. They are very popular, and in 12.47. That entire cluster is considered 15 kV class. And then going beyond that will be 22 kV, 38 kV. Yeah, that 33 kV. So that is something getting higher and higher. You can see higher voltage transmitting to long distance. Transmitting to long distance, you can get much lower loss. Okay, so knowing that medium voltage power, how about medium voltage power electronics? Medium voltage power electronics, you can say, hey, if I have a power semiconductor device, I can process tens of kV. But today, our power semiconductor device, the maximum voltage is only 6.5 kV. So when you talk about 11 kV, that's not possible. So you have to come up with a new way of power processing. Yeah. And then silicon carbide, the wide bandgap devices, the highest voltage I can buy today is 3.3 kV. But 10 kV is already reported in the lab. But they are super expensive. I have one module of 3.3 kV silicon carbide module, and I have to pay how much? Can you give it? Well, I guess 3.3 kV, 700 ampere silicon carbide module. You can give a wild guess how much I have to pay. No, 10,000. US dollar, not rupee. I wish it's a rupee. 10,000 US dollars to pay for 3.3 kV, 750 ampere device. That's impossible for us to promote the power electronics. Yeah, so we better find a good way to deal with high voltage. But that device has been very popular in the high-speed rail. So in the future, India will see that kind of device in your high-speed rail from Japan, made by Japanese company, Mitsubishi. Yeah. Of course, they probably don't pay that kind of price, but from our lab, we have to pay that. And we have to sign NDA. We have to do all the paperwork to purchase that. So high voltage device is tough. So what I propose is use a multi-level inverter, and we can stack up the device with a higher voltage. For example, neutral point clamp, MPC with a diode clamp, flying capacitor, advanced neutral point clamp, and MPC is a combination of MPC and flying capacitor. Okay, I'll show briefly the circuit diagram. And then cascade inverter, which I published in 1995, the first paper showing cascade inverters advantages. Yeah, MMC is a variation of cascade inverter. Okay, so you can also combine them, use a series parallel circuits to make it high voltage, high power. So you can do input series, output parallel, or vice versa. And then we talk about the high efficiency. In that kind of circuit, we need isolation. And now it comes to LLC or CLLC, or the soft switching DC-DC to do the isolation. Okay, so let's move on. The high voltage semiconductor device to make a medium voltage converter, we have done one system. It's the only problem is the voltage stacking is difficult and the package is expensive. As I say, $10,000, we really cannot afford that. And then the availability, you cannot buy it that easily. And the gate driver, design, protection, all these are very challenging. So we typically only use them for high-speed rail because in motor drive, I just need one module, not a utility. I need to stack up to 11 kV, 13 kV. This one, the high-speed rail is only like 1,500. Some of them 6.6 kV, some of them 1.5 kV. But even if you need higher voltage, it's easier to deal with. Okay, and so first look at the circuit diagram. On left-hand side, that is a diode clamping type of multi-level. So in this circuit, if your device can handle 3.3 kV, this one, you stack two of them, you're going to see half of the supply voltage, that VDC. You only see half of it. So you double it up, and then the next one is called flying capacitor. Flying capacitor use the capacitor to clamp the voltage. So you also even out the voltage trace between the devices. So you also equivalently double the voltage rating, but the voltage level is only 3. Okay, then this one is a combination of clamping circuit and the flying capacitor. So I can increase the voltage level to 5. A circuit diagram like S5, S6, you can do 2 in series, like the MPC. So the final one is a cascade. It's the one I'm trying to promote. Cascade, the only problem with this cascade is that VDC has to be isolated, and its voltage level is the same number of switches, but voltage level is the same, and I can use much lower voltage device, and I can continue cascading. Okay, yeah. So the only issue that we need to let me start with MPC. MPC, I actually started very early on. At the time, a custom-made device module when I was with S.P.I.T. S.P.I.T. asked a company called PowerX to build this specific module, stacking 2 devices. Each one is 4.5 kV level. So they stack it up and they call it 18 kV. And I can actually build medium voltage easily with this kind of circuit. And we can provide isolation. And here's the inverter. And here's the phase shift control full bridge converter. Then cascade. Later on, I gave up the other one because the expensive module and limited the voltage range. So we moved to the multi-level cascade. Cascade, your voltage level is just continue increasing from 3 level, and you stack 2 full bridge, you get 5 level and 7 level and so on. Okay. And then LLC, because you need the isolated power, and you can use the most efficient DC-DC converter to isolate. And not just that, you can use LLC, but also what we did is first we use wideband gap. Second, we use extremely high frequency. This one is 1 megahertz. 1 megahertz switching frequency, and you can achieve 99% efficiency. So in the future, you can get even better in the future because the material, that magnetic material made by Hitachi is incredible. The loss is half of what we see the best in the market. So now you can increase the frequency up and you drop the size. The 3.3 kilowatt, I put it in my pocket. 3.3, think about conventional 3.3, that is 33 kilogram. Now, it's so tiny, that's 200-300 gram, put it in the pocket. So, and efficiency, 99%. And that efficiency is complete converter, not just transformer. So time is coming with a wide bandgap device, with that a cascade structure. And then you can do input series here. I make a input series and output parallel. You can do reverse. Wait, here, input is parallel. Output is series. I put it in the wrong diagram, but that's okay. You can do the reverse. So say if I have this size input, that size output, or I can do input there, output here. So you can reverse it. And these two configurations allows AC to be extremely high voltage. You stack it up, and then DC can be any voltage like today, EV. EV, my EV is a 400 volt bus, but the new EV comes out 800 volt bus. So your DC bus can go up to 1000 volt, and then your AC can be any medium voltage. Okay. So that's a modular design, and it's very economical if you can do the modular design instead of $10,000 a module. I can build the entire system with probably a few thousand US, the material cost. So that's the way to go. Okay. So this is one of the examples we built for EPRI about 12 years ago. The input is a single phase 7.6 kV, equivalently 13.2 kV line to line. And we use active from N. And then DC-DC is a LLC converter. And the output is a 450 volt. At that time, this is 15 years ago, only Nissan Leaf was available, and it is a 380 volt bus. So we provide 450 volt for Nissan Leaf charging. And Nissan Leaf is only 20 kilowatt hour. So we have 25 kilowatt is enough to charge it. Within half an hour, we can charge it to full. Okay, so this is early development with a silicon carbide and with 100 kilohertz only. So the size-wise is still too big. Now, the design, we can also do different configuration. You can use LLC or DAV, DC-DC, and then our boost converter for each module is circuit diagram is like this. So that's AC, 760 is AC, and then 400 volt or 450 is the DC, and then you have a control system, sense voltage, sense current, gate driver, and then everything linked with fiber optic, so it's quite safe. Okay. So next is the binary. I want to introduce a newer one. called binary cascade multi-level inverter. So if you need, if you have initially two full bridge, you only get 5 levels. But here, I make it 2 to 0 and 2 to 1. Okay, so I have 2 voltages here, 2 voltage, 2 V, and then 1 V here. And then I stack 1 V and 2 V with some simple manipulation. I get 7 V, 7 level on top. And I have different configurations. And I do charging and discharging for different cells, for 1 V cell. And I can get the 7 level in the end, compared with initially only 5 level. And my waveform is very clean now, getting closer to ideal. So if I stack 3, and I use 1V, 2V, and 4V, it's a binary, right? Binary is 2 to 0, 2 to 1, 2 to 2. If I do that, now 3 modules, I get 7 levels. 7 levels on top, 7 levels on the bottom. So total is a 15 level. So harmonic is getting less and less, and it, total harmonic distortion becomes almost nothing. Okay. So this is the basic theory. You have charging period, you have discharging period for the bottom one. Okay, and then for the same. For 2 to 1, you also have charging. You can do mostly discharging if the source is active. And then 2 to 2, you cannot discharge. That's the one it has to be active source, has to be isolated DC-DC to provide 2 to 2. And then you combine them together, you can do charge balance, even if this one is a capacitor source. Okay. So you have a different configurations, like module design option. I can have, say for example, a active source, another active source, battery, for example. And then I have 400 volts passive source. That's battery I can charge and discharge. And second configuration is I stack 3 cell module to 9 cells module, and I can get 8.4 kV peak or 6 kV RMS. Okay, and then finally, if I want to have different configuration, I stack 4 modules instead of 3. I have 3 active modules and 1 passive, and I go from 2 to 0, 2 to 1, 2 to 2, 2 to 3. Then my voltage level immediately is a 6 kV. Just 4 of them. Just 4 of them. I get 6 kV. Of course, this one could be a trouble because I need to get high voltage device. Others, I can easily buy the commercial device to make it. Okay, so here's the example result for 7 kV. Actually, the output, the left-hand side is light load, very light load. Right-hand side is a heavy load. And I only show 2 kV RMS here, and that's a 1 module. Remember from previous page, that I want to get 6 kV with the three modules. Now, if I just use 1 module, I can get 2 kV RMS. And then THD means total harmonic distortion. It's so beautiful that only 3% THD. The IEEE requirement is 5%, and we get 3% voltage. Current is even better. The current is somehow filtered out by the line, the wire. Okay, So this without filter, and this is the experiment for 100 kilowatt system. And it's very light. Each module, you can carry it. Not like a traditional 60 hertz transformer. It's how many tons compared to this?
Frequency, switching frequency.
1 megahertz. But output is 60 hertz in US. Output of 14 stage is 60, no loss. But the isolation is 1 megahertz. That the transformer is here. That's very tiny. So all the transformer, the little tiny transformer underneath, each one is a 3.2 kilowatt. And I stack all of them. There's no voltage sharing issue because parallel and series power is the same. Input, output power is the same. So I don't have voltage sharing issue. And one module is a 15 level, 3 modules is a 43 level. So basically it's a sinusoidal. Okay. And you can use that for EV charger. We did this 15 years ago. We charged the Nissan Leaf. And you can use that for utility, multi-level. Like for example, you have PV source and you optimize, through optimizer, you get 400 volt or 800 volt bus or even 1000 volt bus, and then make it a utility line, AC line output. Okay, and that is 100 kilowatt, 7.2 kV. Oh, think about it. I calculated 20 kilogram. 20 kilogram. You make it, the other one says 750 kVA, right? That's the transformer built by my partner called Howard Industry. 750 kVA is 5,000 kilogram. 5,000 here. And here it's just multiplied by 7.5. It's only 100, yes?
What will be the life cycle of this?
We haven't put it in the field yet. Yeah. And design challenge. The design challenge for this power electronics, of course, number one, you need a high power, high voltage semiconductor devices. Number two, I have trouble to find the protection. How do I turn the high voltage off? Because it's electronics, not a mechanical switch. Okay, mechanical switch for traditional, I have no problem, but for electronics, it has to be really fast. I have trouble with high voltage power supply for the gate driver. I have trouble for the magnetic components. The Hitachi, the highest volume, the largest volume I can get is PQ 5050. Only 5 centimeter. That's not enough to push a high power. So the component is an issue, and then the grounding, that's creating the noise, and then the parasitic capacitance of the isolation transformers or power supply, and also the hard switching. If I have hard switching, I can corrupt the output inductor or transformer. So I show you, and also high voltage probe, high voltage sensors. There's lots of issues that you cannot imagine to push to medium voltage. Okay, so let me just show one by one. The red one, I'll show you the red colors challenges. First, voltage sensor. The best and very expensive 6 kV sensor is the highest voltage we can get. Very, very expensive, thousands of dollars. Okay, and you would think traditional, how utility did. Utility use a low voltage, that's PT. not enough good for DC sensing. It's only for AC sensing. And then when we put through AC measurement, put it to the high voltage AC measurement, it's all noise, corrupted. Okay, and then the parasitic inductance that can impact the resonant frequency. We say 1 megahertz, but when you bring a wire, that megahertz already changed. Okay, so a lot of issues like this. So we show you here, original is 1.66 megahertz, and then the LC components. And then when you put together with a PCB with the wires, that extends inductance. And then if the frequency drops substantially. Okay, parasitic. And then another challenge, the silicon carbide GaN, they're super fast. It's in the nanosecond range. Nanosecond rise time. So you think, oh, that's good. I can switch at megahertz. No, you're in trouble because that kind of switching speed can corrupt the output can be output signal can be corrupted due to the EMI. Okay, what is EMI? It's the electromagnetic interference. It's very high frequency noise, and you can have the trouble to hear your radio or your music. Look at that. I'm supposed to get sinusoidal, but the motor, think about that motor. Motor, you would think motor is inductor, right? No. For my frequency, motor is capacitor. Because of the winding, you stack so many copper, right? And you stack them together, they become capacitor. So I'm switching into capacitor so that the noise is so severe. EMI, same thing here. The current supposed to be sinusoidal in traditional design, but no longer that easy. Okay. So in conclusion, that I first start with the electrification age, and we're moving from DC to AC first. Now, the AC to DC, and maybe a combined system together, hybrid, and now we have to manipulate between DC and could be high voltage for efficiency concern, and the path toward medium power conversion is not that smooth as you think, but it's your young generation to overcome. we are at the time to fade away, but it's your opportunity also, right? Challenge. Without challenge, you don't have not much to do. So this time, and I work with Professor Pradyumn. He's working on the infrastructure for charging system we use in the medium voltage, and that requires a big team and a lot of resource to do it. So that concludes my talk. Any questions? Any discussions? Yes.
Just for microgrid concept, and while the integration of the say inverter,
Yeah.
how we are using the sampling rates of the signals and how it could change the AC to DC and DC to AC type.
Sampling for us, you have to relate to your microprocessor sampling time. The sampling for us is not that difficult. we with our processing, DC-DC, we don't have to process. The resonant, you don't have to process because it's like a DC transformer. But DC-AC is a line frequency, so I don't have issue. The only issue is the power factor correction. And the power factor correction, that AC side, you can easily deal with 10 or 20 kilohertz because you stack them and interleave. So your 20 kilohertz switching or sampling is good enough. So in this case, you don't have the sampling issue. In grid tie, I want to do phase lock loop, 20 kilohertz or 50 kilohertz is plenty to link with 50 hertz. Yeah. Okay. Yes.
What kind of processors are used in FPGA?
This one we use TMS 320F. That is a 379 series. 377 and 379. The dual core.
So in MV power processing, the DSP need to be taken care differently than the low voltage application.
Yes.
Is there any kind of a
yes,
EMI issues will be
the most difficult for DSP is sensor. Okay. Because I want to regulate the input or output, right? The sensor is a problem. The sensor you bring in, you cannot deal with the traditional type of sensing. Traditional type of sensing, you have sensor next to your power electronics. This is not. The power electronics is far away. It's at least 10 meter or 5 meter away. How do you sense it? How do you transmit that sensing signal back to your DSP? The sensor is critical. Very, very difficult. And sampling, of course. Transmitting 10 meter or 5 meter signal, sensing signal, how do you do that?
Thank you, sir.
Yeah, I can give you an answer. We use sigma delta. Sigma delta converted to digital. So any analog sensing, yeah, send from sigma delta back to the DSP. Then I can regulate. A lot of new technologies that you have to deal with.
Nowadays, this DSP microcontroller comes with sigma delta ADC.
Yes, that TI chip has a 4-channel sigma delta. Yes.
It's a separate unit.
Yeah, yeah, yeah.
Within the.
Yeah, yeah. So temperature, we don't care. Temperature sensing, we still use traditional. Yeah, but for voltage and current, especially that voltage, because you have to regulate the voltage, and you have to do the phase lock loop to tie to the microgrid. Right? Yeah. Okay. Other questions?
Yeah. Hello, sir.
Oh.
You continue.
Yes.
And we are using so many transistors in cascade and everything. How do you deal with the parasitic capacitances and input capacitance of the transistor?
Yeah, that's what I say. Very challenging. When you do the design, you got to have initial design that we build our own bobbin. We design our own 3D bobbin, and then we deal with that parasitic. And you have proximity effect, you have skin effect, you have another one. Proximity, skin, and there's another effect that can be very, very bad. It's air gap, from air gap. So all this high frequency is challenging in terms of design and
I think, sir, Joule's effect you are talking about. Joule's effect. Joule's effect you are talking about. Extra. The skin effect and the Joule's effect.
Skin and proximity, right?
Yeah.
And then there's another one coming from air gap. Fringing, yes.
Fringe.
Fringing effect. Fringing is the worst in megahertz. Yeah.
Radiated noise.
Yeah.
It creates a radiated
Yeah.
Radiated noise is difficult.
Yeah.
Sir, very simple question about it. What about the manufacturing task? Like if your distribution system would be DC,
Yes.
the residential premises is okay because that medium voltage would be covered and the DC supply can be there. But for the manufacturing unit, because in the industrial area and all, like we have the thing that the main transmission could be HVDC and then the distribution would be AC. So if your distribution system is also DC, then what is the concept about it?
Are you talking about manufacturing?
Yeah, manufacturing because the mainly induction motors are there.
Are you talking about industry?
Industry, manufacturing industry.
In industry.
What about the industrial load and all? Because your distribution system is only for the residential area.
The load today, I showed the EV charger.
Yeah.
And similar in industry, manufacturing facility, they may have AC load or DC load.
Right.
Yeah. So your question is
for the AC.
For the AC load.
Yeah.
AC load, you go from DC to AC or AC to AC? That's the question.
Right now, we are going from AC to AC only, no?
Yeah. Today. Today is only AC to AC.
Right.
But there's a trend. There's a trend in the industry that we get medium voltage to the
AC to DC.
To the building with a DC, and then you control the motor drive with a DC. If I have 1,000 volt or 2,000 volt, I have high voltage motor drive. Today high voltage motor drive is quite popular. Yeah.
It's popular, but had it been tried properly?
That was very old technology. 1996, they already did cascade inverter.
Yeah. Earlier it was there. Completely DC traction and everything were there.
Yeah. Not the traction, but for plant. For
plant
industry.
Also. Yeah.
Industry. That was 1996. A company called Robocon. Robocon was then purchased by Siemens. That's in Pittsburgh. They already cascade to 6.6 kV or even 11 kV at that time for the motor drive for industry.
Yeah.
Yeah. Okay.
Okay, so this way this technology can proceed.
Yeah. Yeah. Yeah.
All right. Thank you.
Mm-hmm. So, other questions? Thank you.
We are live streaming the event, and a user has asked, what are the methods employed for thermal management in the medium power systems?
Okay, that's a good question. Thermal management, because we achieve more than 99% power conversion efficiency, we just use a plain heatsink. And we actually post a YouTube showing hundreds of hours of operation and just pure plain heatsink. And we do have small fan to circulate the system, the package. But for device, no heat. No heat device is gallium nitride. Yeah, gallium nitride. Okay. Other questions?
That's all, I guess. Thank you, Dr. Lai.
Thank you.
I'd now like to invite our principal, Dr. B.N. Chaudhary, sir, Dr. Rajendra Sawant, sir, and Dr. Y.S. Rao to present the hamper and the goodies as a token of gratitude.
Thank you so much, sir.
Thank you. Wow, very nice.
Thank you.
Mm-hmm.
This is from IEEE Mumbai section.
Mm-hmm. That's, okay. Thank you. All right.
commercial product in industrial and power electronics. And for the panel, I would like to first introduce Dr. Jason Lai from Future Energy Electronics Center, Director of Future Electronics Energy Center, Virginia Tech, US. Please, sir. Next, I'll invite Dr. Pradyumn Chaturvedi, Professor at VNIT. Please, sir. Next, I'd like to invite Dr. Shashank Wekhande, Application Manager representing Electromicro Systems. I'll next like to invite Professor Ashok Saraf, Technical Director at Syslab Automation. Next, I would like to invite Mrs. Kamakshi Vairagi, Director of Campus Automation. Please, ma'am. And finally, I'd like to invite Mr. Siddharth Chandra, CEO of S.P.I.T. So we'll start by, we all have faced maybe in prior careers or maybe during education, you would have gone through some research projects, you would have done some research projects, right? So a thought might have come in your mind, like what is the end goal of this research? Why do technological companies have an R&D lab, right? Because they want to translate it to product. So that is what our today's topic is going to be, the current challenges that we are facing, that we might face as an education institution in translating a research lab-based prototype to a fully functional industrial product. So I would like to pass around the first question to all our panelists, starting with Ashok Saraf, sir. What gaps, if any, have you identified between educational institutions like us, the lab hosted by us, and technological institutions, the R&D labs of technological institutions? So please.
I would like to first of all tell you that when you are doing a research or any development or in fact any work, the attitude and the commitment towards what we are trying to achieve, that decides to what point you will take that work to. For example, if the mother decides to cook for the fun of itself, she will not produce a food to give to the child. If the batate vade wala just plays with it because there is some funding and some material and doesn't really have to deliver, even if he doesn't have education, for that 15 rupees we expect fantastic results from him. We must ask ourselves a question. As a part of higher educational institution, with so much investment done on us, the funding being given for making us learn, do experiment, what is our commitment? What do we deliver? So think of batata vada. That thought is missing. So you always think of education for a job, or you are studying something for the sake of, my father put me here, things like that. So even faculty looks at very narrow objectives, whereas the whole purpose of putting investment in education in India is to improve the quality of life and to produce economy which requires technology. Now believe me, there is a lot of entrepreneurship here. Uneducated people are enterprisingly living. Absolutely, if you go anywhere in Mumbai, there are so many entrepreneurs, so many people are living on their own. If anybody wants to start an enterprise, what can he do? Even Prime Minister had to do chai wala, because that's the only technology available. Chai wala, vada wala. You want to make a Bluetooth headphone? No technology available. You want to make LED? No technology available. Battery? No technology available. You can't expect entrepreneur to develop all the technologies And you can't expect to fund only the young startup and have all the deep experience to compete with the China. There are people like you, us, who are in educational institution. It is our duty to develop technology and offer it. There was one technology which was offered in 50s to make bicycle parts. Result, till date, India is competing with China in making bicycle parts because public, it was open source technology of making bicycle parts distributed at the cost of one ammonia print in those days. Another technology was given away by Philips to sell their components, technology to make radio sets. The result? All transistor radios at one time were made all over India because technology was available. Technology means circuit diagram, the layouts, the bill of material, inspection plans, how to test it, how to assemble it, toolings, all that is technology. And standards, compliance with regulatory. So these are some of the gaps, starting from commitment to knowledge about what is technology, and then information about how to create a technology rather than just a lab level jugaad or a toy. And I think we know the problem. We just need to commit ourselves by keeping the mother doing the cooking and the vadawala. Thank you.
Yes, that was a wonderful input from you, sir. Thank you for that answer. I would like to pass the question around, the same question around to Shashank Wekhande, sir. Yes, please. Yes. What gaps have you, if any, identified between the research labs of educational institutions and private technological institutions? Are there any gaps in the research?
Sure, definitely. I think the objective of educational institute for research is quite different. You are looking to publish something, presenting papers. I think objective is to make IEEE paper or something research, which may not be a market driven. What industry is looking for is a market driven technology development, and that doesn't need to have any kind of research content in that one. Lot of time the research, particularly in India, goes from the cost point of view. The product is already available. We are not going to develop something absolutely new technology over here. I think the more and more R&D goes in improving it, improving upon the accuracy, improving upon the specs, aesthetics, looks, efficiency, so on and so forth, and more importantly on the cost. So our product, what we are looking from industry, are mainly market driven. We must have somebody to take that product. It cannot be like, for example, I did my PhD. I don't know if anybody has used it or not, but I published probably a couple of journal paper, and I'm happy for that one because I got the PhD. Is that the research I want? Probably not from the industry side. So, but gone are those days. I think probably if your question is relevant, I would say that the research has to be relevant. It has to be market driven. We need to understand that down the line from 5 years now, what technologies will pop up, and we need to be developing the technologies which will be useful to grow the society and India in general. So that's kind of the disconnect which I see. The basic objective itself is different. Educational institutes, they used are for publishing something, and here in industry we are looking to sell something. Number one. Number two, when you do a research in industry, it has to go through a lot of compliances, TUV, UL, safety. If I'm going for automotive products, ASIL, ISO 2006 to 622, and so on and so forth. When we do a product, it has to go through many processes over there, and unfortunately when I'm looking at a academic research, most of the times I see that, okay, I got the results, that's it. But that result doesn't mean anything. It has to be cost effective. It should be good enough to meet the compliance requirement for the industry in what you are working for. It should meet the EMI requirement. It should meet the safety requirement, and so forth and so forth. It may not be the part of the student because in 6 months, years time, they cannot do it, but probably you can create an ecosystem whereby the project can be continued over for 2-3 years over the 2-3 batches, and you can develop a final product which can be sold to the market. That's what I wish we can do. Thank you.
Thank you.
Take forward this question.
Yes, ma'am, sure.
So right now, the sir gave a very good idea, both of them. So they were basically talking about the TRL level of the prototypes, what is there, which is not ready in the market scalable. But apart from this, as of now, what major function like problem we are facing is like labor. Like if some prototypes are made with the advanced technologies, okay, we don't have in India the skilled labors. It is very difficult. So as of now, the industry is going on, right, with the current process, and some new prototypes have to be introduced. So it is a integration is very important, that in that development phase how we can integrate this technology without disturbing the existing one.
Okay.
That is a very important thing. And plus the training to be given to the laborers related to that prototype is lacking.
Okay.
Yeah.
Yes, ma'am.
Thank you.
Yes, ma'am. So, going forward, that was a good input. That was a good perspective. Yes, that's a good industry perspective that we are lacking. The industries might be lacking the labor required for high level prototypes, implementing high level prototypes. Okay. So then, okay. So now, let's consider a case that in any research lab, not just education institute, any research lab, we have a prototype made, and now we want to translate it to a product. So what are the challenges that we are going to face, and how do we go about it? I'd like to pose this question to Dr. Jason.
So your question is for a research lab like we have, and then how do
we go about it?
Convert it to the product?
For the field testing?
Yes.
Challenges.
The challenges.
Yes.
Yeah. In terms of the circuit design, in terms of the paper publication, that's our specialty. In terms of the product development, it's out of our area. Yeah, our knowledge. We know we need to pass UL, pass FCC, pass all the standard, EU standards. Yes, and the school is not equipped to do that.
Okay.
But
so you have industry partners.
But yeah, in my case, I work with industrial partners.
Yes.
I have a company making the induction cooker. So they specify the project, the detail, what's the functionality. So we perform the functionality only. We say we want the power level to be this much, and I want to control it in this manner. And then we design that functionality, and then they take on, continue, they make it a product in the market and sell thousands or tens of thousands. That's a case. Yeah, and then we also develop, myself developed that USB charger, for example. We use gallium nitride. And the same, I just developed to a stage that I prove the power density, the efficiency, all these fancy numbers. And then the industrial partner, they have tens of million products to sell every month. And they will take it over, and then they start measuring the EMI, measuring the safety distance for UL. Yes, yeah. All this kind of stuff, our universities don't equip to do well. Okay, we do measure the waveform, we know the noise, but we don't go into the FCC standard, whatever is a class A or class B. The industrial partner would do it, and they would take actually much longer than the time we develop. Yeah, and the investment is huge. So that's my experience. Okay.
Yes, thank you for your response. I'd like to pass that question to Shashank Wekhande, sir. As you are an industry person, I would like to know your views about it. Like the same question: if we have a product developed, research developed to a prototype, we have a prototype of some product. How do we go about, converting it to full-fledged product, like managing all the user noises, mitigate all kinds of noises? Because in lab we are going to do it in a controlled environment. In field we are going to do.
So I think developing the product should not be your objective. Your objective should be to sell the product, make the money out of the product. That's what entrepreneur does. Sorry, can you hear me? Okay. So what I was saying is that, once again, if you are looking from the educational point of view, publishing research, getting patent, good, great. I would say that if you are looking down the line, technology coming after 20 years, 30 years, that's great. That's good for writing the papers. When you are looking for making a product, objective is to make money. That's it, period. And in order to make money, you have to start way back into your market definition, what customers are looking for. If you develop something which customer is not going to buy, your research is waste, your product is of no use. So probably I will go little one step before, and I'll just go through the whole process if you don't mind. So maybe when you want to do a business, when you want to start something, particularly which is a research oriented, you want a good market input, may not be from one person, may not be from two people. You need some collective information which you think that you can rationalize over some good set of customers, and you will be able to sell the product to reasonably wide market so as to reduce your risk. Number one. So one thing, you have to have your own judgment that, okay, I got these many information. So a lot of times we get the information from customers saying that, hey, I want this power supply operating at this, and we cross check. You are working on so and so domain and you don't need this one. Why do you need this one? So just because the fancy things, oh, I need a GAN based MOSFET drive. Why do you need a GAN for this particular application when you are going to switch at 20-25 kilowatts? So once again, you have to put your own thoughts, intelligence, knowledge to validate what requirements you get. So I'm just talking way before you start your R&D, what you should prepare for, and then the next step comes that, okay, now I do have enough knowledge base, I do have enough design requirements. You start working on your design, you got the design, good. So you all are expert in that step. I understand that you are all technocrats. You understand how to design the product. So I was just giving 2 steps before what you need to do. Then you are good at one of the steps, which is to make the product, do the research and test and validate. So there is something called as a design for manufacturing, what we called as. So when we say design for manufacturing, it need not be what you design, may be manufacturable. You can design something, but it needs say 100 screws to take it off. That's not the good design. Why Apple becomes successful? Apple becomes successful because simple design, easy to manufacture, easy to repair, easy to replace, that kind of thing, and of course long life and all the things. So once again, research is not only good, it has to be manufacturable. It has to meet compliances of your own territory where you are going to sell. Maybe US, then you have to look for the US base. Say for example, ROH is not requirement for India. We are still selling the crappy non-ROHS type of components in India, but you go Europe, you will get arrested if you sell a lead-based product over there. So based on your territory, costing requirement, you have to figure out, and you have to meet those compliance requirement for those countries. So it could be RHS compliance, it could be hazardous chemical things, or it could be electrical parameters such as EMI, transient, surge, noise, vibration, so on and so forth. Once you pass all those things, probably you are ready. Then you need, nowadays, unless you do a marketing well, you cannot sell your product no matter what you do. So हम बोलते हैं कि जो बात करेगा उसका सब कुछ बेचा जाएगा. So if you can speak, even you can sell a refrigerator in Himalayas. That's what we normally call it in terms of marketing type of discussions. So need a good solid marketing also. So R&D is one part of the whole game. All I'm trying to emphasize upon is that when I graduated, I had the same thought that, okay, I became engineer, I have a lot of knowledge now and I can do anything. So next day I wanted to start a company, and somebody taught me all those things which I'm passing kind of to you after many years. So only having a good technical knowledge may not be a good thing. Just think from all the perspectives, that market definition to finally marketing and then getting the funds. Fortunately, in recent times, funding is absolutely not a problem. You just go to anybody and the funds are just flowing for that one. I think the question comes down at this point is to make a robust part, market it well, which your market needs, and then probably you will be able to convert your lab-based research into a good consumer product or industrial product successfully. That's all. Sorry for the little longer discussion.
So basically, what I understood about that is we need to have the motivation same for both research and the technological and education institutions. That if we are going to make a product, we need to make it useful and useful to the market. Yes. That is the main takeaway from what you said.
Right, that's what you should be making the money. Ultimately, you should be make money.
Yes, yes, yes. So, yes. So, Dr. Pradyumn Chaturvedi, I would like to ask you about what trends are we observing in energy density, what we say, research from the advent of EVs in India. Like we need compact batteries for electronic vehicles. So what is your perspective and takeaway on that? And are there any new technologies that we are seeing in batteries? So yeah.
All right, okay, batteries. So regarding this answer, we can say that we are using still lithium-ion battery nowadays, and but they are the most widely used batteries nowadays due to their high power density and energy density still available. But research is ongoing for sodium-ion batteries or aluminum air battery also. Second, third one is the solid-state battery. So these are having some future for electric vehicle drivetrain or to take care of the wide range, because range anxiety is the main thing, which is the main hurdle in is using electric vehicles in India basically. And second thing is nowadays space is not the constraint. Space is not the constraint. So we are having you can say 6 to 7 hours or 8 to 10 hours backup battery for SUV also nowadays in Tesla or other vehicles. So it is already matured. Not in India, we are thinking but it is already mature technology. Okay. So we know that in India, such technology will come after 10 years. All right. So EV is not new. Now we are accepting this nowadays. All right. So one point, and second point, uh, other than battery technology, there is a requirement in India that we should develop sufficient infrastructure to charge the battery, because if we, because still people are thinking that EV will be suitable for city only, not for intercity travel. So it is required actually. So on the highways, on the national highways, we should develop some charging infrastructure within 20 to 25 kilometers. There should be a charging station. At least 10 ports should be there, 10 vehicles should be charged there. It is the main requirement, not battery. Battery is not the concern for electric vehicles. Lithium ion or these are quite okay. So still research is ongoing on new materials for battery. So for example, I am also working on one project. It is a consortium project in which IIT Bombay is developing new battery, sodium ion, aluminum air or solid state battery. And we will integrate this in microgrid applications. So charging discharging cycle and stress reduction, thermal management, cooling system in the battery. So that part is main focus, I think. Okay. So that should be, we have to take care of that thing. Yes.
So I would like to extend the question and ask you regarding the charging time. Are there researches going on? Of course, I'm sure there will be researches going on. And what kind of researches are going on to ensure that the battery is charged faster than before? Like fast charging is an priority, because it's not like petrol that we can just put it in the tank and go. So that's
All
what
right.
I'm just asking.
Okay. So one point I would like to focus here, why we need very fast charging. Within 20 minutes, you would like to charge a battery which will travel or take you up to 600 kilometers. Why you want this? You are wasting time in at so many places just now. 1 hour, 2 hour, wasting the time. For some time it is emergency. All right. Fast charging is not every time beneficial. If I'm not wrong, every time. Fast charging is not beneficial every time. It will put stress on the battery and power electronic components, magnetics, device, as well all the things. This will require very sophisticated design of circuit or system using power converters. So we require, but still we are working on that, and we should take care of this. So the need is that we should develop charging infrastructure on the highways with fast charging. 1 hour full charge is sufficient. All right. Second thing, you should provide some facilities to the customer. They can stay, they can take breakfast, they can take snacks like this, and their vehicle is charging there. So like this, something should be developed. It is required in India. I think. Not only battery electric vehicles. Other than this, there are so many points we have to take care. All right. Means this should be enjoyable. Not stressing.
Yes, yes. I'd like to extend that question once again, and I'd just like to ask, is there something that an educational institute at their level do to help research in these electronic vehicles, all the aspects of electronic vehicles, as we got a point that students here only are for 6 months or 1 year max to max. So, is collaborating with educational institutions beneficial? For that matter, any industry, not just EV industry, any electronic industry, power industry. Is it? What do you think? What are your views about it?
It is obvious beneficial, but one point I would like to mention. I have met so many industry persons. Just now also I am listening to Mr. Shashank sir and everybody. Still there is a huge gap between academia and industry. As Professor Jason is told, he is connected with industries, working with industries. In India, very difficult. If I am having some good concept, good design, good manpower, very good novelty in my converters or controller, but no industry is ready to give the money. No industry. We need in-cash support. Or without that, we cannot develop anything in lab. At least they should support technically or in kind also. They are still not ready. They are telling that you develop this thing within 7 months, 8 months. Not possible in academic institutions. All right, it is a huge gap. So we are ready to give the technology, ready to give the manpower to work on that problem for 1 year, 2 year, but they should support. So industry is not coming forward still. You cannot, even inverters we are importing in India. Good inverter is not made in India. Very good inverter of the very good quality. All right. Even a single LED driver. All right. So we are importing that thing. So why we are not able to do that thing? Due to the lack of the connection between industry and academia. It is missing. So we are talking about separately, but it is required. So this is the major problem actually. So due to this problem, academic person cannot do product level thing. TRL, just now you told TRL. So TRL 3, 4 we can do in the laboratory, but for full testing, thermal testing, EMI, EMC testing, and so many testings are there, that we cannot do. We require 5 CR, 6 CR equipments for that. Not possible. So industry should come forward. They should not take any charge for this testing from academia. All right. So this should be there. Then only it is possible. Otherwise, see, we have to publish the papers. We have to publish patent also. It is required. Other than nobody will know what we are doing. All right. It is required. So, but they should also come forward. All right. So this is my point. If anything not wrong. Yes.
I would like to pass this around to Professor Ashok.
See, I would like to counter that and also support what he said, that what he pointed out from the economy, which is very affluent and he has all the facilities. Even then, he said that there are limitations. So we must understand our limitations, and my advice would be to work on problems, defining the problems, bring them to a chewable size at the lab level. And there are many problems that the industry has and they have no time for working on it. They don't even understand how to define that problem. These are technical problems. So identify such problems, and for that purpose, go and visit the industries around you. Go and ask questions. What are the challenges you have? What problems are there? just have a dialogue, observe what is happening there, how it can be improved upon. Study their designs or circuits and see if there is something you can do. You can do benchmarking of their product with other product and compare the results. That is something that you can do in the lab and prepare a small report. So have this kind of relationship, take the problem, try to study, find some answers and submit the report. And this way the relationship will get built between the institution and nearby industries. It need not go very far also, but this will help you to bring to a level where you will be able to work further when you go to the industry, because you would have methodology. Then you can, as a past student, you can draw resources from here. And then slowly the internship, which is otherwise a big joke, will become meaningful. That the students will actually work on problems, measurements, studying results, studying the reports, and these kind of things which are doable. Don't take on full product development. That can only be taken, as you said, over a period of 3-4 years as a program. And faculty should be encouraged beyond as a postdoc to take on research programs for developing a technology the way national laboratories take on. So you take on a program for developing from scratch, let us say, a charging system, and define the challenges, define the criteria, the way industry will come to you, define what they want, define the targets, and then work out multiple projects. When I was a student in Philips International Institute, there was a project which went on for 5 years of every batch. This was Philips company running a education institute. At the end of the 5 years, we actually made a full-fledged computer. In those days, it was using core memories and it was still microprogrammed architecture. So combining multiple projects of students into a program over a period of 5 years is something that is doable. And that will give you substantial confidence that you can do something. Another thing is have a vertical, have a theme, have an object for every group of faculty as a target of competence and develop center of competence. And you can select a very narrow area. If you're interested in analog VLSI design, still go further and say, what do I want? Can we become a competence center for only doing audio analog VLSI? There is a huge market there. Not a single hearing aid is designed and made here. All are imported. It is nothing but 1-bit audio processor, which is something that you can do. So then you divide the problem into multiple small problems and take help of experienced people in doing that splitting. So define a big program, convert it into small projects, chewable, then combine it together. This will require management capability in the faculty. So teach a little bit of management to the faculty so that they can manage the programs. And this is something doable. I am ready to volunteer till I am available, and I can assure you it is doable. I've done it. It works. Look at the small scale industry. They have no money. They don't even do compliance testing many times, but they deliver value because they survive only on that. There are many small companies who are doing excellent R&D work without putting a word R&D, without publishing any paper, because they have to solve the problem. They have to deliver the solution in competition with China, in competition with other Western countries, because the customer wants it at that price, and then they deliver it. There are many examples. It takes more money for them to print the catalog and go and do presentation like this. I'm doing presentation because now I'm not in the actual work there. When we were working, we can't even afford to spend time to come here and talk to you. And this is the case of most of the small scale people who are doing wonderful research and development. They are not being recognized, and you people should go and meet them. Go and meet the small scale companies. They are in the small industrial estates. You can meet them in the markets and
Sir,
then
I would like
work
to
with them.
interrupt that I am one of them, a small SME. So we are basically working on the same platform, what example you gave.
Correct.
Yeah, the same thing is there. It's a very small setup.
Yeah, see, but you require some support. And if you take a student as an intern, You have to spend more time in sitting with him or her, rather than he taking away problem and sitting and working on it and then coming back to you.
And
So
so
that sense of commitment and attachment should come. There used to be, when I was a student in IIT, there was one L.R. Subramaniam. He used to run a instrumentation company in Ghatkopar. And we used to visit him. He was an ex-IITian and he used to welcome us. And we learned a lot of practical things by visiting him on weekends. That process has to be revived. The students and faculty should go to industry and sit there. There was one person in our batch who was quite aware about this. I have gone with him and explored the Vadala Industrial Estate scrapyard to find out what kind of things are there in the industry. And I learned so much from it. When I was in IIT, on Sundays, we went around and looked at the scrapyard. So these are kind of processes of interacting with the industry, because we could not enter the industry. So we looked at the scrapyard and understood what kind of things are happening here.
Right. Thank you. That was a wonderful input. I really appreciate you pointing out that it's our responsibility as an education institute as well to, go ahead. Yes, sir.
And I can assure you, this is not a burden, it is not a work. It is fantastic, enjoyable. What I'm telling you is about 52 years back, and I'm still enjoying it. So it is something that will drive you throughout the life. So start doing it. It's a lot of fun. Engineering and really delivering engineering solutions is fantastic. It is most enjoyable thing you can do.
Yes, sir. Thank you. Thank you very much, sir. So, moving the discussion forward, I would now come to a point of view from investors. So, I would like to ask Siddharth sir, like you are the CEO of S.P.I.T, you have lot many startups under you. So I wanted to know, I wanted my audience also to know, what are investors looking at when when products are being made by the startups. Startups are generally like research. They have done some research and they are translating to products. So what are investors looking at?
Thank you for that question. Firstly, it's a privilege to be a part of this diverse panel and such good thoughts to hear from such experienced academicians as well as people in the industry. I feel the common pain point that we have started off with the discussion has always been about talking about a gap, right? There seems to be a gap which exists between industry, and there seems to be a gap between the industry and the academia side. How do we cross that? So I feel, firstly, before I answer your main question around investment, I wanted to talk about this thing that you can start building in islands. If you're an island, you can go about, you can start building things, but after a certain point of time, there's going to be a limit that you reach. If you think about it, it's a question, open question. Do you know how much of a similarity we have with the DNA of a chimp? Any guesses? 20, 30%. Anybody else? It's 98.8%, right? So we are prone to copying things as well. So after a certain ecosystem kind of builds out, it's easier for us to kind of replicate things. It's just how it is, it's a nature. Where a lot of power and value comes, which I feel is associated with progressive growth, is in bridges. When you're able to bridge systems, when you're able to cross a bridge, and I think the most powerful bridges happen when you are taking or you're talking about people who have experienced both systems in certain ways. If you're bridging two systems, they should have a knowledge about the two systems, and we are able to come in and create that bridge so that people can start thinking differently about the same problems, right? That gives you a scope to grow beyond where you were thinking. And I think that is where a lot of progress and innovation can really thrive. So coming to your question as to what investors are looking for, so whenever we are building, I guess, something inside a research domain, people are very fine-tuned and they go very deep with regards to creating something. But at times, we don't live in an ideal world. So people don't use the same product in the way that we visualize they would. People have different ways of utilizing it. They can abuse it also. They can also use it in completely different ways. When WhatsApp was made, it was made with the intent of sharing status messages. But they realized that people wanted to basically talk. That evolved, right? LinkedIn was made because there was a problem with regards to sharing resumes, but it evolved into a social network for professionals. So the use case kind of evolves, and I think when you are, number one, able to try and experiment and have a lot of users use what you're building and gain feedback from that, that can really, really come up with allowing you to grow your product. So to answer your question now, which is what investors are looking for. Investors are investors, which means that they're giving the time and money. So they want to give their time and money to things which will be able to scale, right? Which will be able to stand the uncertainties of what people, how people are going to behave when they are interacting with the product, how it will scale over uncertainties of economic uncertainties or geographical and environmental uncertainties, how it can phase it out. So when an investor is looking at from their lens at a product that they would want to invest in, they're looking at all these things. One of the prime things which we in fact look at is not even around the product. So when we sit in a panel, one of the rubrics that we have in a measurement is who are the founders? What are they bringing to the table? What are their experiences? And the quality of founders and the thought process can allow a person to get convinced even if a lot of things do not hit the check mark. So that is how the thought process is with regards to investment. Of course, you have to do your work with regards to telling that you have thought about how you're going to have your product being used by people, what are you going to estimate with regards to your financial planning around it, what the product actually is, what it does, and how you're able to present it. So if these things are fall in place, there is a very, very high chance an investor will say yes.
Okay. Okay. That's a wonderful answer. Let's have a real applause for the panel discussion. I'm thankful for all the panelists to have this great discussion. It was a good one. I'd now like to have audience ask the questions to panelists. If there are some regarding the topic or anything else regarding industry, please. Any questions? Yes.
Yeah, good evening, sir. Few of my students had worked on a project called Smart Ignition Control for to prevent bike accidents. Now the question is, most of the cities, people do not wear helmets, and if Ola is trying to bring in some sort of invention in their bikes, like how unless you don't wear a helmet, the bike won't start on. Now the question is, if the implementation is done, but we are not able to try to connect with the industry partner. Although I'm trying to connect with Siddhant and a few more industry people to bring into practice. That's what you really said, connecting academia with industry. Saraf sir already mentioned to connect with small MSc, but this is a large scale project, like bringing it actual to implementation. Like ignition control has been done. Now, if the person starts the bike after wearing helmet, the person will remove the helmet as normal Indian tendency is there. And in those cases, it may happen that it may hamper to an accident. But instead of doing it so, instead of closing the bike off, turning the machine off, let us give some sort of intimation through different technologies like IoT, connecting the bike with an IoT device, giving a signal to the RTO or so that they will penalize the person. Because in India, value of life is zero as compared to money. Money has more preference. You give a fear to life, like you have been charged high, and that will create a sort of fear in the mind that they should wear a helmet. Now, what I'm trying to have a problem is, I'm not able to connect with industry. So what could be the solution to this?
What problem are you trying to solve? Is that a problem?
Sir, problem is already solved.
Wait.
Yeah.
The problem that you chose to solve is not a problem. If that is the case, then there won't be any takers. So wait a moment. You're trying to make two-wheeler driver wear a helmet. Government of India and the entire government mechanism failed in convincing Pune people who made a lot of halagulla about it, and they scrapped the rule.
Agreed, sir.
Okay?
Agreed,
So
sir.
point is there are areas where there are lots and lots of social and the perceptions. So while you're working on the problem, first of all ask yourself a question, go around and validate your problem. And is that a real problem, or is there some other
It's a
problem?
serious problem. Many
No,
of
no,
my
no.
family members have died also, sir.
No,
That's what I'm saying.
that is still, there are plenty of accidents of different sorts in
Okay.
which plenty of people's relatives have died, right? Is that whenever you try to bring in any product which requires regulatory compliance and acceptance
Exactly.
and government enforcement,
Exactly.
then there are lots and lots of other procedures and also issues involved, social, political, corruption, and all that. So the point is, don't necessarily try to say that the solution is there, and now I'm only trying to look for the industry. The industry will say, boss, you try to get that rule sanctioned, then I'll come and make your
But
product.
that will, sir, unnecessarily demoralize the student who are looking for a new future, sir.
No. It is not demoralizing. It is really taking up the problems which are really, really required and which will generate value. Any problem which is going to be policing the society is not necessarily a value. A value can be generated by better empowerment of the minds of the people so that they feel safe and they live
Exactly,
safe.
sir. Exactly.
Not by policing it, not by putting pokayoke, so the vehicle can't start if you can't do salam or something like that.
I've seen, just to add to your
that is
contents.
philosophy.
Yeah.
If your practical problem is you have a solution and you want an industrialist, then look for industrialist who is looking for something to do in the vehicle market and try it to your ideas with at least 10, 15 industrialists.
Okay.
And then probably you will hit upon somebody and who might take that and may not take anything else but a controllable ignition. That may be the part of it. Or maybe the helmet, if it is a good helmet.
Yeah.
He might accept a part of it. He might accept the whole thing. Or he might even accept your capability to solve the problem and say, "Are isko baaju mein rakho hai. Can you do this? Can you make an intelligent helmet which will do, which will tell me the state of his health and do assistance so that I know whether the driver is in problem." So there could be many things which will emerge. As I said, the use cases will evolve, and your capability to be open to go along with it will decide whether the industry takes a solution.
Thank you so much, sir. Thank you.
Any more questions?
So I think your question was how to connect to industry. That's what I understand. And without getting into the complexity of is your product good or not, I fully respect his view. But I'm assuming that you have done your market survey and you have figured out how to do a product, and probably you have finished your R&D and now you would like to market it. How do you get into that market? I think that was a very specific question. Now this may not be related to this particular helmet case, but it could be something for a different product, and I'm taking this as a generalist question. So my answer is going to come from that background, not for a particular product specific. So number one, particularly for automotive industry, you will never be able to go alone. If you want to try to, you need somebody who can walk you to the doors over there. The ways to get that one, probably find out who supplies them. Already who supplies them, who are the suppliers. The suppliers could be distributors from electronics industry, something, but automotive industry, because of the safety regulations and all the things, usually anybody getting in and just getting into the automotive is really difficult. Very few examples, probably SEDMAC is one with their very high background, they were able to succeed. But most of the times, I mean, I'm not going to talk about a company and names, but just look at Bajaj and their surrounding companies. Just look at Hero, their surrounding companies, and you will find out a pattern that what it is, and then I'm not going to talk more than that. So point is that you need somebody to take to them. And the best way to figure out is that you partnership with someone who is already a distributor to them, who is already selling. Give markup to them. So you give 10% markup to a distributor, let them sell the parts. So when I'm in this industry for last probably 15 years in automotive industry in India, it's a lot easier if you have a right people with you to sell your product in that industry. And how to get? Probably we can talk offline, or you can figure out your own research, but that's the easiest way. Pay somebody commission and ask them to do your sales. You are basically doing your production. If that is your objective, do your production, manufacturing, R&D, and then let somebody handle all the nitty-gritties of sales, service. I mean, once again, I'm not talking for a specific product of helmet. I'm just talking in general as a product line. And then there are after sales warranties. So automotive industry is very, you know, they need 10 years of working and all that stuff. So they don't believe on somebody individual person like that. So you need who has them trusted resources or trusted relations with, and that's how you would be able to get it over there. Thank you.
Thank you, sir. It's a good question. It's very difficult to get the network. I'm working with IIT also. I'm doing their marketing. I was a professor in engineering college for 20 years and then shifted to industry. So initially I faced a lot of issues. From last 8 years I'm working with them. And don't give up. Jabardast follow-up is required. And your network is your net worth. That's what. Thank you.
For I have a lot of collaborators, including the automotive companies.
Yeah.
When we develop the advanced technology, they are not looking for commercializing it. They're looking for what you can do, what this technology can do. And then when we look at the existing product, it's very poor.
Yes.
Yes, it's compare efficiency. We're 98%, they're 92%. And no comparison in terms of performance, but would they use your technology? No.
May or may not. Yes.
No, they have tier 1 supplier.
Yes.
They have tier 2 supplier.
Yes.
They have all tiers. And we're just R&D. And for them, they just want to see, hey, what you can do.
And I can learn from you.
And then they learn from us. And then they go to tier 1, say, hey, you do it. Yeah, you do it like this. So that's a kind of connection I have, but it's for your. Okay, thank you.
Okay, so we'll conclude this panel discussion and move ahead with our keynote lectures.
Thank you very much.
Thank you, panelists. Now we'll have a brief session of development of EV charging infrastructure in India under Maha EV National Mission by Dr. Pradyumn Chaturvedi. Dr. Pradyumn Chaturvedi has received his BE degree in electrical engineering from Barkatullah University, Bhopal, India in 1996. His ME degree in power electronics from Rajiv Gandhi Technical University, Bhopal in 2001. And he's done his PhD degree from the National Institute of Technology, Bhopal in 2010. I'd now like to invite Dr. Pradyumn Chaturvedi.
Thank you so much. First of all, I would like to pay my thanks to the IEEE Bombay section, joint chapter of PALS IES, and chairperson Dr. Savant and S.P.I.T. Team authority to invite me for discussing. No problem. All right. For discussing some topic. So as the request from Dr. Savant, so he has given me this topic that you talk on this development of EV charging infrastructure under some Indian government scheme. It is the call, it is now open actually, this call is open now. So to develop charging infrastructure for Indian roads and cities, because we have already identified some cities for a smart city project like this. So this is very required call actually. So just now we had so many discussions, so many points came out from our panel discussion also, from previous keynote also, and so many points. So I would like to just mention few points why this call is open and why this call is opened by Government of India and what are their significance. And just now we talked a lot for academia industry collaboration. So this call is basically to enhance that industrial academia collaboration. All right, so that's why we will focus on this. So this call is nothing but it is, now we know already that DST SERV, this board is now known as ANRF, Anusandhan National Research Foundation. All right, so ANRF. So now every scheme is now under this call. So they have launched this mission for advancement in high impact areas, MAHA. MAHA means big, huge. So MAHA program with EV mission as its first priority. So this is the first priority of this mission actually. So after this, they will also have open some call for other missions also. So EV mission is the major focus of Indian government because it will cover all aspects like battery. Second is the machines and drives, motor drives control, drivetrains, and design of automotive or car, that thing, and different in-service control also of EV. And third one is the electric vehicle charging infrastructure development. So these are the three main verticals under this call. So this will focus mainly on this, this point basically you can say, to develop self-reliant and developed India. So this is the main focus of this call. Make in India. Don't import small items or components. So everything should be made in India. So this is the main focus of this call. This is the call for 5 years basically, but government of is giving funding for 3 years. So they are focusing on developing the product in the laboratory with at TRL 4-5, not beyond that. 4-5 is okay, all right, it is okay, sufficient. So we can design, simulate, analyze, and develop low-scale prototype in the laboratory, test it perfectly. Suppose, for example, some converters, so we can test it and run it for some hours, 50 hours, 100 hours continuously or something, and we can test for thermal, cooling, stress testing, EMI, EMC testing, everything we can do in the lab or nearby industries. So this is the target for this. And after 3 years of development of this TRL 4-5 level of the product, industry will come. So Government of India will publicize the product we developed in the laboratory in the university, and they will contact industries and they will publicize throughout this call, and industry will come to you. है ना? So there will be very good connect between industry and academia after 3 years as the fruitful outcome of this call. So then we can develop TRL 8, 9 label of the product. So that will be more useful in every aspect of the call. So this call is basically, as I told just now, that this will cover the wide spectrum from EV means EV is nothing but battery, converters and motors and their control, everything. And all the control will be inside the, you can say that can be implemented by onboard chargers, their controllers or FPGA, DSP as well. So battery, motors, controllers, power electronics, chargers and grid interface. These are the main focus or components which we will have to focus mainly. So single person cannot do this thing. So this call will, there is a big consortium. I'm also one of the member in one big consortium led by some IITs. In this 4 IITs, few NITs, few private institutions and more than 6 industries are there in that big consortium. In that call, suppose for example, we will prepare the proposal for 25 CR total, including all battery, motors, controllers, power electronics, chargers, grid interface. A single person cannot do this thing. So mechanical engineer, CSE, EC, electrical, physics also, chemistry also. So everybody will be the part of this call. So this is a huge consortium, interdisciplinary and inter-institute collaboration. All right. So this call is very needed actually. So just now everybody talked about this thing. So this is the answer for that actually. So, but last date is Monday for this call. All right. So, so no issue. So, but just now, as per request from Dr. Sawant, just I would like to just mention this call and its main purpose is that in this presentation we can get so many areas which we can take for our research and development. All right, so this is the everybody knows about this thing.
Who should participate in this?
Anybody can participate. NIT, IITs, private institutes like S.P.I.T. also. Anybody can participate in this. Industry, institutes, R&D organizations. Everybody is free for that. So this is the basically for to achieve net zero emission target and transportation sector's role in that to achieve that net zero emission target and economic and environmental benefits, we have to go for smart transportation like this. So we have the target for this net zero up to 2070. All right, it is not very easy task. And if we will talk about this net zero, then still battery and those are also having some emissions. All right. So there is a scope, huge scope for research and development in that research. So before going forward, I would like to mention one point: research. Like somebody told just now, research. You are not doing anything new. All right, industry will not go for very new technology, which will be very complicated, very complex circuitry, complex control technique. They will not take that thing. They will go for simple thing, cost effective and efficient. And nowadays main thing is the reliability also. So industry will go for reliability. All right. So reliable converters and products should be there. All right. So for this we can just talk about in the last of the presentation that we are developing some fault tolerant converters like this. So these are the main challenges and some opportunities for developing this type of system. Cost, limited range and range anxiety, all right. And third is the global innovation also. So main thing is the cost and these range anxiety. So to take care of this thing, cost is all right, no problem. But this is the main problem, range anxiety. So that we can take our electric vehicle intercity travel also, that we have to take. So for this we need to work on battery and power converters, BMS, and main thing, we should be able to develop charging stations within some specified distance. It is required. Otherwise on the highway, you will go from Bombay to Nagpur via highway, Samruddhi highway, huge desert. Even you cannot find any single tree also. all trees are cutted by government of that thing to make the highway. So if your battery will fail on the way, you are you can say helpless, nothing. So there should be something within 10 kilometers or 15 kilometers that you should have some charging stations with some amenities, some small restaurant or something like this. We should develop that thing. All right. Yes.
Because unless you build the charging infrastructure, EV would not be promoted.
Yes.
Okay. Yes. And unless you have a EV, the people are not investing into building a charging infrastructure.
Yes.
It has really become a chicken and egg problem.
Obviously. Yes.
So can you comment on this?
Basically, we are.
Who should invest into that infrastructure, building infrastructure?
In this.
If they are not having players, because initially they have to spend the money and wait for 5 years till the technology is getting us in a normalized situation. Number of vehicles should increase. Is it not?
Yes, yes, it is obvious question. Yes.
So how to break that circle?
So just now we discussed at some point that means there is different vehicles from different companies, different sockets, different charging infrastructure, different batteries. So there is need to standardize or to generalize the charging standards basically. So this is the main thing. So for this to develop this thing, government of India is investing huge money, but private players are also there. They are also ready to support and invest the money in that case. But main thing is that we have to generalize the concept of charging socket and every charging gun, everything. So this is required actually. So investment is coming from Indian government and private players also. Both are ready to do that. But main thing, and even we are already having EVs in the market, huge numbers we are having. But these two are the main challenges. To take care of this thing, we have to develop more and more in charging infrastructure on the highways. It is required. All right.
So how many components are really being designed in India out of any standard charging station? How many components they are really built in India or made in India?
I know.
There are manufacturers who are making
Yes.
those components.
Yes. I know so many companies are there. They are very startups, new startups. They are making their own components.
I'm just asking.
Yes. They are manufacturing in India itself. In my consortium, there are 2 startups are there. They are ready to implement and develop full charging infrastructure, full charging stations. Nowadays, we are having 2 guns in one charging station, 2 gun in India, 2 charging guns are available. Now we are proposing multiple guns with some variable voltage also, not very wide voltage range, but little range. All right, so that any vehicle can come off any voltage, then they can charge from that charging stations. So they are ready to implement that thing. So they are having in-house development in their companies. So it started already. All right. So I will just come to that main call, what they are having this in this call. So in this call, basically this is the multi-institutional call, multidisciplinary call, and multi-investigator call. So in this case, they are having these 3 verticals. So this is the slide in which we can take 3 verticals. Number 1, some EV batteries and battery cells. Second, power electronics, machines and drives, EMD. And third is the electric vehicle charging infrastructure. Out of 3 verticals, now we will focus on the areas where we can work. So I think in this hall, mostly are the person from power electronics, mostly, or power systems or EC, communications. So they can also take some note of this thing. So this call will be in the consortia mode under EB mission for establishing electric mobility nodes, e-nodes. In India, there will be 3 nodes to be created, 3 nodes. One node will be in battery, one node will be on PEMD and one node will be on charging infrastructure. Suppose 20 people are submitting proposal under battery. So they will form one LPI, lead PI in India, and 20 out of 20, maybe 4, 5, 6. Government of India advises, they can suggest, okay, you go in this e-node. They will suggest. So 20 people will submit some proposals, and those advisors will suggest, okay, you are fit in that e-node. You go there and work there. For example, 30 people will go for PEMD, so they will suggest, okay, you can do work good in this node. Go for that node like this. है ना? Somebody for last one. So this is a very good idea or initiation of Government of India. All right. So for example, person A can submit the same proposal in all 3 nodes, because in all 3 nodes there is a requirement of power converters, BMS, battery charging, discharging, cycle control, everything in all 3 nodes required. These are not separate. है ना? So they can suggest, okay, you are fit in that node, go. Your converter control is fit for battery charging, discharging only, not for drive control. So they can suggest. So this is a very good call, I found. So e-nodes, in each node, you can say there will be maximum 3 to 4 academic institutions can collaborate like this. 4 are the maximum limit. All right. And one LPI will be there, and all PI will be there from so many institutions. So from one college or industry, 3 person can be at max, can participate. So now as I told just now that TRL 4 should be there in the laboratory, and that you can elevate to TRL 8, 9. So within 3 years of time span, they are targeting that we should be able to obtain TRL 5 to 7. All right, for this case with industry support, and after that they can take industry, and industry can go up to TRL 9. They can go up to that point. So there are some schemes. I will not read all these because it is already available on the internet. ANRF.maha-EV mission. You can find out on that. So, but there is scope for R&D in cell technology for battery. All right. So just now we have discussed about this. Which type of battery will be suitable for that? So cathode active materials, and this you can say high nickel content in the battery. So somebody can also work on this. So chemical person can do only in this case. So we cannot do anything as the power converter engineers. So some innovative silicon-based and metal anode development, or electrolytes and additive, including some non-flammable electrolytes and so many things. This is not my area, so I cannot read this thing. So, but you can take, somebody can take this, these areas. Some R&D on lithium-ion battery technology, somebody can do. So here they are focusing mainly this thing, last 2 sentences. TRL 2 to 4 is the target basically. So in battery, we have to find out this some energy density, some power density based upon that thing. So compactness will be there in the EV or that vehicle. And beyond lithium-ion battery, there will be some so many different chemistry are there. Sodium-ion battery, then multivalent ion battery, and SSB. So this is the latest SSB. Maybe future, maybe this SSB, maybe. So chemical person can comment on this very specifically. All right. So AI enabled discovery of cell materials, highly accelerated battery testing mechanism also. So this is the battery pack design or thermal management also for battery. All right. And in the last of subdomain of this vertical number 1, battery circular economy. So second life battery cycle, or how to reuse the battery. So it is again a major challenging task. And third one is the how to dump the battery, after full use of the battery. Now it is first use, second use, third use, it is ended now. So how to dump this? So in future, this will be the major challenging task. Second vertical is the power electronics drives, PEMD. So in this case, we have, this is the area where we can contribute. So development of new motors, which will not depend upon the magnets or rare earth magnets. All right. So nowadays we are developing some new motors like SYN-RM, this synchronous reluctance motors and axial flux motors and so many others. So SRM like this. So we will go for some efficiency improvement, power and power density also, or high torque density also in the EB. High torque density is a major task. So in this SYN-RM, this one, if you can just see this SYN-RM design, its rotor design, this will be very, very, you can say, very beautiful design. SYN-RM rotor is very beautiful, you know, having some fancy type of structure. So we can do this design very effectively in ANSYS software or something else. All right. So then we can also develop some new material for the motor components, for magnet, for conductor, and for insulating materials. So person from metallurgical and material science, they can also collaborate here. So in some consortiums, they are also in the team. All right, they will develop some new material for conductors, insulations, and magnets. All right. Okay, and also we have to also do this for widely of varying speed and operating conditions also. Then some EV motors, then again we can say integrated and low power thermal management. So thermal management is the crucial and very important part of EV mission. So mechanical person who is doing on thermal management is very, very important person nowadays. All right, thermal design, thermal management is very important. All right, effective and optimized thermal design. Without this, it is impossible. In battery, magnetics, power electronics, motors, everywhere thermal engineer is required. All right, so he is the main person behind all this. Then motors, then, all right. So now this last one is our interested topic. So design and development of high voltage DC inverter, more than 800 volt, with some advanced power electronics and control techniques. All right. So nowadays it comes now. So to reduce the size of the conductor or to reduce the losses, all right. So it is required to operate or develop a medium voltage DC grid. Like professor also told that we should develop some charging infrastructure of 1 kV DC, 1000 volt DC. It is required, all right, for fast charging and to reduce the losses also. All right, it is required. So, and for that we need some motors which can work at that level also. All right. So using SiC and GaN device based power electronic converters is again required, and for this component packaging and PCB label design also is required. Okay. So like SMT and other techniques, 2-layer, 6-layer PCB design, and high current density also to be developed in the PCB during the PCB design. So second point is the high yield, you can say manufacturing process of GaN wide bandgap devices, and all right. So this fourth point is the development of high voltage inverters in this range up to 1.5 kV DC. All right. So again, in motor sections, we have seen that multi-phase motors. So in EVs, multi-phase motors are also one task they have given, subdomain they have given already. So multi-phase design of the motors. So for that, we need some high voltage inverters or power supply design for that. All right. And fifth is you have to develop some, nowadays, all right, we are going for this V2G, G2V or V2X type of applications. So we need some bidirectional power converters for this. All right. So we will come to this after this, that which type of converters will be there, which are useful for future grid. And we should be able to do this thing. Number 6 is the major main point, number 6. We should be able to develop, we are developing some converters, choppers, buck converters, boost converters, buck boost converters, so many things. But main thing is that we should be able to develop some modular converter, one module, all right, which should be scalable. We can give that module to industry, they can scale up, they can multiply those modules, they can connect those in series parallel to increase the current and power level of that. Modular converter architecture, inverters and onboard chargers, that can be deployed in different vehicle platforms. It is the main thing. Nowadays, one system is only applicable for one vehicle only. All right. So we should be able to develop some chargers or some systems which will be generalized, can be used in any vehicle. So there is a need of standardization and you can say to make some common policy for that or some standards for that. It is without that nothing can be done. Without that, everybody can do at their own way. There should be some rule or standard as per that everybody has to follow that. Like harmonics, there is some rule of IEEE standard that we have to create some converters which will generate harmonics below 5%. It is a rule. Anybody cannot violate that. All right. So like this, we have to also develop some rules or policy here. So now they are framing that policy now. And this in-service condition monitoring and health management, it is already developed already in some vehicles, but required in all vehicles, from low power or two-wheeler to SUV and everything. It is required. And last one is the design development of thermal management system with safety also. So these features are required. If you will go for the vehicle which will have all these features, very costly. So we have to develop some low cost or cost effective solutions for all these. In India, if you will import all these things, now I think we are importing all these things, all the services we are importing, all services. So it is costly. So if we will develop this thing in India, make in India, then these will be very, very cost effective. I think 40% cost will be there, I think, for that. Then after this, this is the main thing, this fault tolerant drives, fault tolerant. So that means if, for example, you are traveling to some place, to other city, so some fault occurs in the converter or some motor or some controller, that what will happen? So you have to wait for service engineer on the way. So this fault tolerant drives, so this is the main challenging task to meet out the reliability of the EV mission. So we should be able to develop fault tolerant converters and fault tolerant drives so that system will not fail ultimately. So you will be able to develop the reliable solution for this. Low cost, make in India solution for fault tolerant EV mission. So it is the main thing. All right. So what industry is doing, they are doing for inverters or for converters, if fault occurs, they are using some spare unit for that, spare unit. But there are some topology developed already. We have already developed in my lab also some fault tolerant multi-level converters having some less device count, switching counts, which will work perfectly, which will give full power, full voltage under one switch fault condition, two switch fault or multiple switch fault condition also. If fault occurs at 2, 3, 4 switches, then still it is working fine. So there are some new topology developed already. So that can be used by industry also. All right. So this is very important point. And thermal also, here we can also say thermal. Thermal management system is always everywhere. All right. So second vertical. Now we will come to third vertical. So first is battery, second is PEMD drives or their control, and third is the now again very important EV charging infrastructure. So for this we need to develop this thing. Now we discussed so many points. So in this case we can see wide range of power converters here. So there is a requirement of developing universal infrastructure socket and its standardization. This is the main point which we have to take care. Ather, Ola or whatever EV company is there, they are having their own socket. So that cannot be charged with any common socket. So there is a need to develop some universal socket for that. AC charger, DC charger, level 1, level 2, level 3 charger. So we should be able to develop some socket which will take care of every type of charging station or infrastructure. We can go anywhere, we should be able to charge our vehicle. So the socket should be like this. It is not at present in India. All right. So this is the major task of this call. All right. Then low cost and lightweight charger also. Then again, this fourth point, it is very important nowadays. So we have to also develop this SST, solid state transformer. है ना? So I think Professor just discussed this few points on this in his talk already. So SST is the major, you can say, component of EV charging infrastructure for future grid. Future grid will be based upon SST. All right. So because this is having that front-end converter, take AC, then DC. All right. Then again DC to DC or DC to AC. So in one stage, two stage, or three stage conversion will be there with isolation in between. All right. So we have to provide high frequency isolation in between so that we will be able to generate or implement DC bus at two different voltage levels also, or DC bus of variable voltage, adaptive voltage can be also possible in that case. All right. So this is very promising technology nowadays for future grid SST. So this is again low power charging. So in the laboratory also, means we have also developed in the Nagpur also that 25 kilowatt SST already tested. Okay, that is working fine. And battery swapping, again very difficult task, but in this call they are having this. So somebody also proposing this thing, you know. So maybe after 3 years we can see in somewhere, you know, in this e-node, we can see that battery swapping system will be operating after 3 years.
Vida already uses it. Vida
Already
has a battery swapping system.
Yes. Where?
You don't have to wait for 3 years. Kilo.
Yes. All right.
So their two-wheeler has a removable battery.
Yes. So that is very good concept actually.
You don't have to wait for 3 years. Now it is available now.
Yes.
It is in the market.
But then it will be all over India. This can be implemented. Then yes. Yes. All right. And high power charging also. So small modules can be developed, and then we can integrate to develop high power charging, 250 kilowatt or more than that also for national highways using this SST and SiC-based devices. And new concept is wireless charging. So how many of you are thinking wireless charging is promising or beneficial? Wireless charging is beneficial, required, or just fancy?
How much efficiency?
Very less.
So no.
Yes.
If it is at 98%, I would say yes. If it is 70%, I would say
Yes. All right. Okay. All right. But this again one call, they have opened this subdomain. Yes. Yes. All right. So they are targeting static only, static, not dynamic wireless charging. Static. Static vehicle will be there, then it can charge only like this, not dynamic charging. All right. And again, then we have to also see the impact of EV charging on the grid side. So power quality issues also we have to focus on this. So in this case, real-time monitoring of that, integration of the photovoltaic, wind, RES on the charging infrastructure also we have to take care. So these are the points which we have to take care, because if we are targeting 80% of the vehicles will be electric vehicles after 10 years or 20 years, then what will happen? So huge RES and huge number of EVs on the road. So all are non-linear loads. So what will be impact of those on the main grid? So this we have to take care. So this is again a very challenging task. So this will require development of some controllers or some converters or some techniques, filters or something, some issues. which will take care of this thing, power quality issue. So, and again, this cable development for 1.5 kV also, low cost, make in India. That is the main thing. So this is the basically EV development in India, basically from 2011. So they have just made some consortium or council for this EV mission. Then till then, now they are framing one by one, slowly that policy and standards. And now this call came. So it is not a single day job. So they were working since around 10 years to achieve that target. And now they opened all the calls. Now they specified all the areas in every 3 verticals and subdomains. All right. So these are the bodies who can fund for R&D in this area. Ministry of Power, and they have their own responsibility also. What they will do, or they will fund for what? They will fund for these specific roles or responsibilities. For example, if this BIS will define the EV charging standards only, and if you will talk about some, you can say, EV tariff will be decided by SERC only, and if guideline for using the charging infrastructure or development of something, suppose you will develop some charging converters, so who will control that charging converter performance or standards? So though MOP will be there, so they will define, okay, your charger is okay now. All right. So there's another call. MIT is there. MIT is there. MIT in India, they are giving some targets already. They have given some ratings, voltage, power, current ratings. So as per that only, you have to develop that converters or chargers for level 1, level 2, level 3 chargers. So this is the main thing. So in this MIT call, other than this call, they are asking 20% in-cash support from industry in that case. All right. So again, difficult task. Suppose we will develop some medium voltage DC grid connected some EV charging infrastructure for national highways with PV and battery. Then cost is around 3 CR, 4 CR. And 20% means 60 lakh, 70 lakh, 80 lakh, for example. So industry support should be in cash for that much amount. So difficult task. All right. So TRL means everybody knows about this thing now. So this is the only, just now he wanted to just me to deliver or to show something about this call. What is this call and which area we can focus? These are the areas which we can take as a research also, R&D. It is a very, those who are not able to submit the proposal, they can do work in the lab. They can do on these aspects or these subdomain areas. All right. And they can also come to some nearby in NITs, IITs also. So they can come to me also. All right. So if you anybody interested, they can also come to Nagpur also. So we can do this collaboratively also. We are having some basic equipments, modules, converters, controllers. We are having that already. You come and use that. So we welcome all of you. All right. So after this, just now I would like to just mention about my laboratory. So recently we have developed this multi-port SST, and these are the converters we have developed from active front-end converter, this active front-end converter, line inductors, everything of 25 kilowatt, and then dual active bridge in this case, and multi-port converters at output of this thing. So at different five different voltages, this can work. So this is looking like this from outside. Multi-voltage. No, multi-voltage. It is multi-voltage. So that you can have isolated 5 different voltage levels. Yes. So 2-wheeler, 3-wheeler, or 4-wheeler, SUV, truck, bus. So anybody can come. So all are adaptable voltages. So you can charge your vehicle. So 96 volt, 110 volt, 400 volt, and last one is the 750 volt. So these are the voltage ranges of each. These are not wide range, specified, low range, low variation of the voltage. But we are getting this thing. So it is working fine and deployed in IIT Bombay site, this thing. So applications are different, you can say. In so many applications, this can be used. This concept, not the same. And this is scalable. It is 25 kilowatt. So we can scale up this thing up to 250 kilowatt. Within the same structure, we can have all the features of 250 kilowatt, this thing. So for this, I have taken help of one industry for this, for fabrication of this panel, metering, cabling, that thing, or MCB putting everything. But all the converters, controllers designed by my students, all right, in the laboratory. So PFC is working fine, and these are the converters inside the SST using some multi-level topology, and some fault tolerant design of the converters also inside that, so that any fault occurs, then the inverter will take care of that thing. All right. So no need to replace the full inverter. If fault occurs, then no problem, it will work fine. And after some time, you can replace that switch, no problem. This will bypass that switch. All right. So it is deployed completely at IIT Bombay site recently, before only on 15th of November only. So one patent published already on this. So my student Saraf, so we have done one interesting thing in this case. In existing system, in which you are using 50 hertz transformer, you cannot replace that exactly. But in the presence of that LFT, you have to insert this SST. All right. So what will happen to both of them? So interaction between LFT and SST will be done, so that sympathetic inverse current phenomena be captured and be tried to mitigate that phenomena. So based upon that, one patent published, and other than this, work is ongoing. This is the recent only. Other than this, there are so many developments already done in the laboratory. So these are the projects already we are working in the laboratory of Pearl. So one Indo-Taiwan, one India EU Horizon 2020 project, and one recently got project. This is Saraf Center for Energy Storage. So again, all are using SST technology with some new converters, controllers, and optimized controllers, everything. So now, Miss, I request all of you, those who are willing to do some research, not having the equipments in their laboratory, they can come and use that, and we can do some research collaboratively. All right. So this is the, you can say, just now Miss, this is not for technical talk, Miss. So as requested by Dr. Sawant, I have prepared these slides. Yes. Otherwise, I could also give on SST design development also of this. All right. Yes. Yes. So this was the call actually for EV charging infra development. Yes, sir.
Will they extend the date of Monday?
I don't think so. Till today, not extended.
Extended?
I don't know. Done?
I don't know. Is it extended? This is extended one.
Mighty call they extended till 5th of December. Mighty call. Not this. Yes.
I shared 2 days, but there the names were IIT Bombay, VNIT Nagpur, all IITs. No small colleges.
No. All eligible. Eligible.
So you want to write, we still have 1 day.
No. Eligible.
You write a proposal, you still have 1 day.
To them and they will forward there.
No, it is not the case. It is not the case. In my consortium, we have one private college already there. Sir, in my consortium, we are having already one small private college. They are the PI. They are PI. No, it is first call. First call.
So you are NIT is a e-censor?
No. We are the part of one e-node proposal given by some IIT.
This is how you are submitted.
Yes.
Or you are already clear.
No. Submitting.
So you are scope and some IIT, main IIT, the hub.
Yes.
And you are appealing us to also be a spoke.
Yes. In India, only they will give only 3 e-nodes: one battery, one drives, one charging. Yes.
Mostly
Hmm.
it will be in IITs.
Yes, yes.
That
Maybe.
will come to IITB.
That I don't know.
He will come to IITB. That we don't know.
That we cannot.
Depends on whether IITB is interested or not.
Yes.
If you want to do private one, you can do. Better product will come out and we'll sell the technology. Right?
I will support the components.
Yeah.
Yes.
Look, I will
You
support.
started from scratch, and how long it took for you
I've been operating
for this particular
Showcase
setup?
that thing. This was a 3.5 year project total. But if you, I will tell you effectively, then it took around 2 years. Design, simulation, and procurement of the components, and till this stage, 2 years. 2 years. The students have done this. Saurabh, Aditya, and Harish, and Sajid, they have done this thing.
He is giving. No, sir, it will come again.
All right. Any more questions?
You sell the technology and earn money from it. Rather that is taking a government grant. Okay. Thanks.
Okay. Okay. Thank you so much. Thank you.
In fact, this today's event, there is no wonder if I say like this. There is no wonder if I say like this, ki this event is happening because of Pradyumna sir. I will tell you the reason. Because the joint chapter of PLS IES of IEEE Bombay section has been established by this fellow. He is a founder chair in 2018, 19. And since that chapter has established, we could, organize this function under that banner. Okay, so credit goes to Dr. Pradyumna. Thank you. वो दे दो. And I really thank all the audience and their support. Chalo. जाओ. Yeah. Sir. इधर आओ.
Thank you, Dr. Chaturvedi. Next up, we have a session on remaining usable life for power devices and risk mitigation by Professor Ashok Saraf. I'll now be introducing Professor Ashok Saraf. Ashok Saraf, based in Pune, Maharashtra, is the technical director at Syslab Automation. He brings experience from previous roles at Patel Science and Technology India, Jain Irrigation Systems Limited, KPIT, and Konkan Corridor. Ashok Saraf sir holds a 1962-1985 Master of Electrical Engineering and Communication at Philips International Institute, Eindhoven, with a robust skill set that includes business strategy, product development, embedded systems, electronics, and program management. Thank you, sir.
Thank you. Can you show the photographs which I shared? Yeah. No, it's okay. Good evening. I will not take too long. I have no presentation. I have only, and I'm not from power electronics. I'm basically from communication, digital, and entrepreneurship development and so on. But lately I've been forced into power electronics because there is a tremendous shortage of manpower in industry, and I'm since 1982 I've been working as a consultant to help indigenous technology development and surviving on that, and happily. So I end up doing this study. So today I learned a lot about power electronics. In 2023, last year, I had gone to attend one conference in Sweden, and I uh, I attended one of the lecture where I took pictures, and this was very, very interesting eye-opener for me. It was about federated learning. You see, the power electronics is growing in all these areas. And you heard, Professor, that it is basically a new way of electrification. The entire energy that we will use will come through magnetics and semiconductor. All these devices, they are physical things. They have life, they may fail. And depending on where it is used, the impact of that failure can be disastrous, can be extremely dangerous. So it is important to know, it is strategically important to have full control over safety and to understand the remaining life and replace these devices in time. So there was a project, you can Google on this Power Size D. This is a European Union project by consortium, by combining the information about the failure modes of the power semiconductors. About 23 universities and 39 industries and 72 million euros provided by government. It is industry sponsored project. None of the data which is going to be used by people or the manufacturers in Europe for predicting the life based on the models that they will generate based on the data will be available to us. None of the devices that we will end up using in India would be qualified and will be certified and known to have certain known life. We won't have the models of those. Can you understand the implication of this? And no wonder that Europe is investing so much money in generating that piece of knowledge. And the process of generating these models is not very complex. They just did large number of experiments of RDS on change by cycling through thousands of cycles of high voltage, high current switching and find out the behavior of the RDS on and find out how that fits and how the remaining life can be predicted, and by using normal AI technique have evolved models and validated those models, and all the devices which will be used by manufacturers will have to be undergone these kind of tests to generate those models, and then only they will be used by the manufacturers. Now it's going to be a proprietary data. I don't think we are going to get access to that data. Can you, as an educational institution, do something to do such kind of research projects, which are not very high tech in terms of design or something? Go to the Power Size D, whatever is published information, read about it. 1 minute. See, they did the power cycling test device, this kind of test equipment, and the data. How do I go? So this was the institute, RISE, Research Institute of Sweden. They seem to have done that project. These are just photographs from that conference in Gothenburg in 2023. It was about electric vehicle. Yeah, how do I move this to next? So the method development, failure analysis, physics-based models, machine learning and hybrid modeling. This was the technique that they used. Wire bonds in power devices. These are some information pieces to explain what are the failure modes they have observed, and more important point is that they collected the data. So the objective is utilize full lifetime of the product, future reuse and repurpose, increase safety and reliability, and more efficient product based on the remaining usable life prediction. So if that is approaching certain period, you replace them. And if you don't, then you are at a risk of sudden failures when the vehicle is being driven or when the lift is going up and down, or some operation is going on in a theater. There are many, many cases when the failure impact can be disastrous. So this is all I wanted to say to the community of power electronics, to take interest in such nationally relevant, important research ideas and activities to generate usable data, and that is a contribution to the industry. It doesn't have to be a new technology or something like that. Develop methodology, develop even methods of reducing the heat loss between heat sink and device, better compounds, better technologies for fitment. We talk about lots of electric vehicles. There is a requirement for making connectors, making pure copper buses, high voltage buses, contactors, switches, methods of testing those, methods of testing and validating the components that will go in this power electronics. All this is engineering. Engineering is not just power electronics within quotes, devices and the models and the MATLAB. Engineering is all about the real solutions, the physics of it, the mathematics of it, modeling of it, understanding of it, and observation and passing on that knowledge to the rest of the community. Is this understandable? Karoge? Thank you very much. Bye. Thank you for giving me opportunity to come to you. Thank you. Any questions, please? Yeah, but why? Because power electronics is going to be one single impact factor for the entire ecosystem and magnetics. And if you neglect that, it is extremely important, as important as the food quality or more, because more and more power is controlling us. And all of that is going to go through power electronics. So I wanted you to feel aware about it and see the importance of that. Right, but yeah. The failures of this semiconductor is a bit tricky because they are small, they are inside, they are hidden, they are not mechanical. Mechanical things are, you can hear them failing, you can feel them failing. These electronic things, they are all hidden inside. Any questions? This ANSYS gave that presentation, I think, because they used that technology. And what I learned there was interesting. Not for this product, but some other product. Normally, you do full mathematical simulation, right? So it requires a lot of computation. If you develop a complex thing, then complex simulation to go through all kinds of scenarios and predict the behavior, you have to run many runs of the simulation with different loads, different environments, different parameters, and so on. So the total computation becomes more. So they develop a technique which you might have read about called ROM. So they create a reduced object models. So they did functional modeling based on the data of certain simulations. And then instead of using a physical simulation, they use a functional simulation as the next layer of simulation for other cases. So the speed improved a lot. Computation become less expensive. Now, on top of that, based on the results of that, they develop the AI models. So then they use those AI models. So the entire car simulation with the power drive, mechanical, motor, transmission, electronics, the embedded part of it, and the software, all of that under simulation through the ANSYS system as a common model, which I think has been released last year. They could simulate with this AI-based technique of first mathematical, then functional, and then AI models. So that the work that could be done in, say, 50 years could be done in 50 hours. That kind of speeds have been now achieved. So you can improve the complexity of your systems, integrated systems, mechanical, electronic, software, everything put together, like what is happening in the electric vehicle. And that platform was very interesting. I saw the presentation of that in the same conference. So,
life cycle or failure
What I think, what I learned from there is basically. Uh, See, what I learned is that if you focus on thing which can fail, then that thing go inside the physics of it, find out the reasons by which it will fail, then find out the behavior through which it will be cycled in its life. Like if it is a device, it will be cycled through on and off cycles. Then observe the impact of that behavior and then identify where the failure comes. Then do that on multiple devices and then identify, compare, and then create a failure model which is statistically based on the database. And based on that, you then predict the failure, assuming that the devices are going to be of a same kind. If there is a different kind, then you create a new model. If the model fails and if the data tells you that your model was wrong, then you stop the devices until the new model is developed, and otherwise don't use those devices which are unpredictable. And if it is a system, then of course multiple component failures will have to be modeled into system failure. Then system being subjected to real stresses will have to be compared against the cycling data that you got and then find out where the current status is. And then that is another higher level problem which can be taken up. But this is something which is strategically important, I think. Thank you.
Thank you, Ashok sir, for your incredible insights. I'd now like to invite Dr. B.N. Chaudhary sir and Dr. RRS sir to felicitate Ashok sir. I'd like to request Dr. Rajendra Sawant sir to remain on the dais to present this certificate of acknowledgement to Khadija Batan for presenting her paper. As we reach the end of such a beautifully educational and insightful session, I'd like to invite Dr. Rajendra Sawant sir to present a few words of gratitude.
So at the outset, I thank all the participants who have really participated with the full, clappings and whatnot, questions. So it is a really interactive sessions, different sessions. So it is a really interactive conference, one-day conference that has happened today, which was not expected by me and not expected by my colleagues, supporters also. But, and on top of it, we have feather on the cap that Professor Jason Lai has accepted our invitation. Okay, and some senior IITB alumni professor like Ashok, Saraf has accepted our invitation. And as I already told you that we really got a very good support from our alma maters like S.P.I.T, our IEEE Bombay section. They have really supported wholeheartedly for this. So we have not charged a single penny from the participants for organizing such a wonderful 5, 6 sessions. The panel discussion, we try to have people from diversified areas, and we succeeded in that. In fact, I would be really requesting all of you to fill a feedback form. Okay, we'll be sending you a Google form, and please religiously give a feedback for this particular event. If you really got some benefit out of it, or if you want to comment something to improve our way of doing the organizing the events. And IEEE Bombay section is always is nice to host, because they have several societies, and they had one scheme of research colloquium. And let's say there are societies like Optical Society, there is Society of Power Industrial Application Society, or there is a Society of IEEE Communications, there is Society of Signal Processing. So all those societies, they have different research colloquium. One day, a conference like thing, keynote addresses, discussing recent trends in technology, okay, bringing the people together. This is the whole purpose of such type of research colloquium. And we have just slightly changed the name as Research Conclave. At the outset, I also would like to thank our Honorable Principal Sir, Dr. B.N. Chaudhary. He has wholeheartedly given me a support of using infrastructure here at S.P.I.T, and also some kind of other support, financial support also to some extent. Okay, but his heart is big, and most of the students, volunteers, okay, nonetheless they are working. Their submission is going on. They are very busy in end-term submissions, doing a lot of things, but wholeheartedly they are with me, and they are working with me since last couple of hours. I still remember 48 hours. They are with me continuously, bringing here and there, going, putting banners, handling IT stuff, etc. Okay. And also my colleagues, professional colleagues who are really supporting me. And at the outset, I would say that Anand Gharpure, our chairman of IEEE Bombay section, he has really supported me and encouraged me to have a big collaboration with industry and the academy, and bringing them together. And I hope that I'm partly successful in ending of this session. Thank you.
I'd like to thank all esteemed guests, faculty, and all attendees for actively participating and interacting in today's session. Certificates to the attendees will be sent online, and tea is served outside the auditorium. This is your host, Samrit Shetty, signing off. Thank you.
Yeah. Once again,
Standing validate.
no, you sit. You sit. Once again, on the behalf of S.P.I.T, IEEE Bombay section, I would like to put my thanks to all of you for sparing your Saturday and being here. Many of you have attended most of the sessions. Today we had a wonderful day, starting from Professor Chandorkar, who had taken us into very, very niche topic of debugging the multi-core based embedded systems in real life applications. the those event-driven or time-triggered systems, and debugging of that is a real-life issue. Only the people who are into the development and making a development board hands-on acknowledge those issues, right? And though he has taken, he has taken us a very broad view of that debugging. Then Shashank's lecture, Dr. Shashank, who carries both academic as well as research experience. Shashank was my fellow colleague when we did PhD together at IIT Mumbai. I was Fernandez student, Shashank was Agrawal student. And we both had a privilege to have two guides. I was first a student of S.K. Pillai, and he first joined with Dinkar Prasad. Pillai retired and Prasad left Bombay, and that's why we had to have another guides. But I got a friend for lifetime. His friend, family member, and I know his contributions to that company. He's building his team and responsible for all Eastern countries, developing a team he has developed a small but powerful team at Pune, and now asked to develop similar team at Hyderabad. His lecture was very informative and talking about the new devices that have come, and for a demonstration he has come with one small circuit. He has several such circuits developed at Pune in his lab. Those who are from Pune or who anytime you go, feel free to step into his lab. Surely he will show how in a small space a world-class product can be developed. That is Shashank. Thank you, Shashank. And thank you for being with us, sparing your Saturday also. I know how valuable Saturday is for you. Right, you are from industry, and you look forward weekends, and thanks for coming from Pune to Mumbai, being with us and sparing your weekend. We are greatly honored to have a presence of Dr. Lai. Thank you, Professor Lai. I understand. We hesitate sometimes traveling to Nagpur or traveling to Pune, but on one call, you accepted our invitation. You are already on someone's guest, and now you have become guest, right? So thank you so much. Thank you so much. We really appreciate your presence here, right? Already you are on a tour to the Nagpur for a month, and on the behalf of entire society, I really appreciate your presence in the country with our centrally funded institution. And on the top of that, on our request, you have traveled from Nagpur to Pune and sparing, and you are here with till Monday. We really deeply appreciate your presence. Thank you, Professor. And what a lecture you have given. I was wondering, you started with DC Dynamo, right? Tesla, Westinghouse, and then Edison, that DC-AC war, and so quickly you have come on the topic and taken us to the beauty, and particularly that binary cascaded H inverter, and how beautiful, with the 3 stages, seven or levels can be achieved. It was very interesting, Professor. Thank you so much. And Professor has several contributions. If you read what is Professor Lai, you will understand what person you have listened to today, right? Then we had Chaturvedi ji. Chaturvedi ji, I feel guilty that I have missed this project. I was wondering why you were not invited 1 month ago, right? Now you are saying the project is closing on Monday, and I was wondering can S.P.I.T participate, right? But still we'll try. there is Sunday still remaining. So tomorrow we'll try to submit something to that project. Would like to be spoke. Hopefully IIT Bombay will be hub, because looking at the power electronic big group there and energy systems department, surely either IIT Bombay or IIT Delhi or ISU will be one of the hub. Will try to participate in that. Thank you for taking through that project. And Professor, we should not miss such projects. You are R&D coordinator, right, of S.P.I.T. So you take that thing. We should not miss such opportunity. And lastly, Professor Saraf, thank you for triggering the minds. It's just not those complex geometries and complex, deep technical drives. Sometimes simple problems can also be of of very tremendous importance to the industry, and work can come out. So he triggered you just with thought. Even a life prediction of the gadgets or components could be the issues, and there can be different techniques, mathematical, statistical, NN base or whatever. So they say, they say we had a feast of sweets today, isn't it? आपण म्हणतो पंचपक्वान्नाचं जेवण घेतलं. We had five. We had five desserts being served, right? And it was quite a learning to me, and surely to many of you as well. And I'm really thankful to all the speakers. And I must thank all the man behind this, the chairman, Power Electronics Society, IEEE Bombay section, who is busy all the time. Professor works 12 hours a day and 7 days in a week. That is what Sawant is. And sparing still within that, we are a small institution, but the kind of work he's doing is comparable to the CFI institution. I will request you to spare some time, visit his lab and see the kind of work. We got 7 millions from DST for technology development, and we are committed to deliver a technology to the industry. And we are sure next year we will deliver that product. He spared still time and managed this event, and he's chairing the IEEE section. I'm sure this year would be the most vibrant year for that chapter of IEEE Bombay section. I'm sure about it. Right? He will set the benchmarks, and those benchmarks, it will be difficult to touch or to go beyond those benchmarks for his successors. And this is what his commitment is. Thank you, Dr. Sawant, and thank you, your and team of Professor Sawant, his research associates, and my students who volunteered themselves. And thank you, your term ended yesterday, and your friends are busy in preparing the exams, and here you were making preparations for this event. I really appreciate this commitment. You have exam 5 days down the line, but on the call of teacher, you are sparing your day and giving your services. We value those. Thank you so much, dear students. And so, thank you once again. Have a safe travel back home. Enjoy the Sunday. We have got a stable government.